Welcome back to Scientific Discovery Hub, your gateway to the most mind-bending breakthroughs and celestial wonders inches the universe. Buckle up, because today we're diving into a real-life sci-fi adventure, an interstellar comet named 3I Atlas, hurtling through our solar system at 58 kilometers per second, faster than a bullet fired from a spaceship. And get this, Mars is about to get a ringside seat to its dramatic solar showdown. You've probably heard of Oumuamua and Borisov, the first two interstellar travelers we ever spotted. Now, 3I Atlas is the newest and possibly most fascinating visitor yet. Discovered in July 2025 by NASA's Atlas telescopes, this icy time capsule comes from the ancient thick disk of the Milky Way, a region older than our solar system itself. But why does this matter? Well, every fragment of gas and dust it releases as it nears the sun could hold clues about how planets form inches-distant star systems. Plus, it's the first chance to study an interstellar comet from Mars, thanks to a close flyby in October 2025. In this video, we'll unpack how Earth-based telescopes and Martian orbiters are teaming up to track this cosmic fireworks show. We'll explore the icy chemistry of 3I Atlas, think carbon dioxide, cyanide, and even nickel vapor, and what it reveals about its alien origins. You'll learn why Mars, with its clearer line of sight, might spot details Earth can't, and how scientists trace this comet's journey back to a 714 billion-year-old corner of the galaxy. Spoiler, it defied expectations by arriving from the south, challenging our assumptions about where these visitors come from. We'll also tackle the physics of its escape from its home system, the math proving it's truly interstellar, and whether it might shatter under the sun's glare. And yes, rest assured, this isn't a doomsday scenario. 3I Atlas poses zero threat to Earth, but it's a treasure trove for science. So, whether you are a space enthusiast, a curious student, or just someone who loves a good cosmic mystery, this is your front row ticket to a rare real-time event that's rewriting the rules of planetary science. Hit play, and let's journey together through ice, fire, and the endless wonders of the universe. Don't forget to like, subscribe, and ring the bell so you never miss another voyage into the unknown. Let's begin. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies swirl inches slow, eternal dances, a solitary traveler emerges from the darkness. Imagine a comet hurtling through the void at 58 kilometers per second, a speed faster than a bullet fired from a spacecraft. This is 3I Atlas, a celestial wanderer born inches the crucible of another star system, now sweeping through our solar neighborhood with the urgency of a messenger from the unknown. Its arrival is not merely a spectacle, it is a profound reminder of the interconnectedness of the universe, a whisper from the deep past carried across billions of years of space. Why does this interstellar visitor matter? Because every atom of its icy nucleus, every flicker of its coma, holds secrets about the birth of planets, the evolution of stars, and the chaotic beauty of the Milky Way. What stories does it carry from the depths of interstellar space? And how does its fleeting passage challenge our understanding of the cosmos? As we peer into the night sky, we are not just observers. We are participants in a dialogue spanning eons, a conversation written inches light and time. 3I Atlas is the third confirmed interstellar object to traverse our solar system since humanity first began scanning the heavens with modern telescopes. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, stationed in Chile, its discovery marked a pivotal moment in astronomy. The comet's hyperbolic trajectory, a path that curves sharply under the sun's gravity, before escaping into interstellar space, revealed its true nature, an alien wanderer, unbound by the gravitational leash of our star. Unlike asteroids, which are rocky remnants of planetary formation, comets like 3I Atlas are icy relics from the outer reaches of their native systems. When the sun's heat warms their surfaces, volatile ices sublimate into gas, creating a luminous coma and a trailing tail of dust and plasma. This transformation turns 3I Atlas into a glowing beacon, a cosmic lighthouse illuminating the void. Its origins lie beyond the familiar realms of the solar system, inches a region of the Milky Way known as the thick disk, a sprawling ancient structure where stars older than the Sun drift inches chaotic orbits. The comet's velocity, exceeding 58 kilometers per second relative to the Sun, is too great to be explained by interactions with planets or other solar system bodies. Instead, it carries the imprint of its stellar cradle, a velocity that suggests it formed inches a system far removed from ours. 3I Atlas joins the ranks of 1I Oumuamua 2017 and 2I Borisov 2019, the first two interstellar interlopers ever detected. Yet, unlike its predecessors, 3I Atlas is an active comet. Its nucleus cloaked inches a veil of gas and dust that glows faintly against the blackness. This distinction makes it a unique window into the chemistry and dynamics of distant planetary systems, offering clues about the building blocks of worlds beyond our own. The study of 3I Atlas transcends the boundaries of astronomy, touching on the very essence of planetary formation and the history of the universe itself. Comets are time capsules, fragments of primordial material that have remained largely unchanged since the birth of their parent systems. By analyzing the composition of 3I Atlas's coma, scientists have uncovered traces of carbon dioxide, water ice, carbon monoxide, and even cyanide gas and atomic nickel vapor. These molecules, forged inches the cold crucibles of interstellar space, hint at the chemical diversity of exoplanetary systems. Could such materials have played a role inches seeding life on early Earth, or do they represent processes entirely foreign to our own cosmic neighborhood? Moreover, the comet's age, estimated at 7.6 to 14 billion years, places it among the oldest known objects, inches the universe. Older than the solar system, 3I Atlas predates the formation of the Sun and its planets. Its journey through the Milky Way may have begun inches a stellar nursery, long since scattered by cosmic tides, carrying with it the echoes of a bygone era. Such an object challenges our assumptions about the longevity of planetary debris and the resilience of comets inches the hostile environment of interstellar space. If 3I Atlas survived for eons, what other relics of the cosmos await discovery? And what do their trajectories tell us about the gravitational architecture of the galaxy? Perhaps most profoundly, 3I Atlas forces us to confront our place inches the cosmos. For centuries, Earth has seemed a solitary world, adrift inches an indifferent universe. Yet the comet's arrival reminds us that we are not alone, that the stars too exchange gifts inches the form of wandering comets and asteroids. Every fragment of 3I Atlas is a testament to the shared history of the Milky Way, a reminder that the ingredients for planets and perhaps even life may be more widespread than we imagine. In its brief appearance, this interstellar traveler becomes a symbol of unity, bridging the chasm between the familiar and the unknown. But how do we detect such a fleeting visitor? How do we distinguish a comet like 3I Atlas from the countless asteroids and comets that orbit within our own solar system? The answer lies inches the ingenuity of our instruments and the vigilance of our observers. From the vantage points of ground-based telescopes to the eyes of space observatories like the Hubble and James Webb, astronomers have developed an intricate web of technologies to scan the skies. Yet, even with these tools, spotting an interstellar object requires serendipity and precision. The story of 3I Atlas's discovery is as much about the challenges of observation as it is about the comet itself. In the next segment, we will explore the tools and techniques that enabled humanity to glimpse this cosmic traveler and the obstacles that nearly hid it from view. The universe is a vast and silent stage where the actors rarely speak. To decipher their movements, astronomers rely on a symphony of instruments and techniques designed to pierce the darkness. For 3I Atlas, its discovery was no accident. It was the result of decades of technological advancement and collaborative effort. Telescopes like Atlas, the Hubble Space Telescope, and the James Webb Space Telescope, JWST, form the backbone of this cosmic detective work. Yet even with these marvels, detecting an object moving at 58 kilometers per second across the night sky is akin to spotting a firefly inches a storm. How did astronomers not only find 3I Atlas but also unravel its mysteries? The answer lies inches the marriage of innovation and persistence. When 3I Atlas was first observed on 1 July 2025, it was faint and distant, appearing as a mere speck of light against the crowded backdrop of the Milky Way. The Atlas system, designed to monitor near-Earth objects, played a critical role. Inches its initial detection, Atlas scans the sky twice nightly, capturing wide-field images that are automatically analyzed for moving objects. This rapid cadence allowed astronomers to identify 3I Atlas's motion relative to the fixed stars, a key clue Inches determining its trajectory. However, confirming its interstellar origin required follow-up observations from other observatories, including the Zwicky Transient Facility Ejection and the Very Large Telescope VLT. The comet's position near the galactic center, a region teeming with stars and nebulae, posed a significant challenge. Its faintness and location, Inches a dense field, meant that automated detection algorithms struggled to separate it from the background noise. It was only through meticulous manual review of archival data that pre-discovery observations from late June 2025 were uncovered, allowing astronomers to reconstruct its path with greater accuracy. These observations revealed that 3I Atlas had been moving on a hyperbolic trajectory all along, its velocity far exceeding the escape velocity of the solar system. Once its interstellar status was confirmed, the hunt for answers intensified. The Hubble Space Telescope, with its unparalleled resolution, captured high-contrast images of 3I Atlas's Comet, revealing the subtle glow of its outgassing nucleus. Meanwhile, the James Webb Space Telescope, operating Inches infrared wavelengths, probed the comet's chemical composition, identifying trace amounts of carbon dioxide and water ice. Ground-based observatories, such as the Lowell Discovery Telescope and the Canada-France-Hawaii Telescope, contributed spectroscopic data that confirmed the presence of cyanide and nickel vapor molecules, rarely seen Inches such abundance. Inches, solar system comets. Together, these instruments painted a picture of a comet unlike any other, its origins etched into the very atoms it released. The detection of 3I Atlas underscores the importance of global collaboration. Inches modern astronomy. The comet's discovery involved contributions from professional observatories, amateur astronomers, and automated surveys, each playing a role. Inches the unfolding story. Amateur astronomer Sam Dean, for instance, identified pre-discovery observations. Inches the Atlas archives, demonstrating that citizen scientists remain vital to the field. Similarly, the rapid sharing of data between institutions, from the Minor Planet Center to the European Southern Observatory, allowed astronomers to piece together the comet's trajectory. Inches real time. Beyond the technical achievements, 3I Atlas highlights the limitations of current detection systems. Its faintness and proximity to the galactic center nearly obscured it from view, a reminder that many interstellar objects may go undetected simply because they are hidden. Inches plain sight. Future missions, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, promise to revolutionize this field by scanning the sky with unprecedented depth and frequency. With its ability to detect objects as faint as magnitude 24.5, LSST could uncover dozens of interstellar comets, transforming our understanding of their prevalence and origins. Yet, even with these advancements, the fleeting nature of interstellar objects remains a challenge. 3I Atlas will vanish from Earth's view after October 2025, its closest approach to the Sun occurring during solar conjunction. Only Mars orbiters may capture its final moments near perihelion, a sobering reminder of how quickly these cosmic messengers slip away. For now, 3I Atlas stands as a testament to human ingenuity. A single thread inches the tapestry of interstellar exploration, woven by hands both earthly and celestial. But what of the comet itself? Beyond its trajectory and detection, 3I Atlas carries a story written. Inches ice and gas. Its nucleus, shrouded. Inches a coma of escaping volatiles, is a relic of a distant world. In the next segment, we will delve into the anatomy of this interstellar traveler, exploring its structure, composition, and the forces that shape its luminous dance through the solar system. What secrets lie within its frozen heart, and what can its chemistry reveal about the birth of planets. Inches other star systems. At the heart of 3I Atlas lies a paradox. A body so ancient and alien, yet so familiar. Inches its behavior, like the comets of our own solar system, It is a fragile world, its surface sculpted by the relentless pressure of solar radiation. But unlike its solar system counterparts, 3I Atlas carries the fingerprints of a different star, a different epoch. Its nucleus, a dark, icy core, no larger than a small mountain, is encased inches a shimmering coma of gas and dust, a temporary atmosphere born of sublimation. To understand this comet is to peer into the raw material of a distant planetary system, to witness the alchemy of ice and sunlight Inch's action. The nucleus of 3I Atlas is a mystery cloaked Inch's shadow. While Hubble Space Telescope estimates suggest its diameter ranges from 0.32 to 5.6 kilometers, the true size remains uncertain due to the overwhelming brightness of its coma. This ambiguity is not a flaw, but a feature of cometary science. The nucleus is a hidden engine, its activity masked by the surrounding haze. What we do know is that the nucleus is composed of a mixture of ices, primarily water, carbon dioxide, and carbon monoxide, interspersed with organic compounds and silicate grains. These materials, preserved for billions of years, offer a snapshot of the conditions Inch's its parent system, where temperatures were low enough to freeze volatile molecules into solid form. The coma of 3I Atlas is a dynamic phenomenon, constantly evolving as the comet's surface interacts with the sun. When solar photons strike the nucleus, they heat the ices to temperatures above their sublimation points, transforming them directly from solid to gas. This process, known as outgassing, releases jets of vapor and dust that expand outward, forming a diffuse envelope around the nucleus. Spectroscopic analysis of these gases reveals a rich chemical tapestry. Carbon dioxide dominates, with traces of water vapor, cyanide, and even atomic nickel. The presence of these elements is striking. In solar system comets, water ice typically outnumbers carbon dioxide, and cyanide compounds are rare. 3I Atlas, however, defies expectation, suggesting that its formation environment was colder or chemically distinct from our own. The tale of 3I Atlas, though faint, is another testament to its cosmic origins. Composed of ionized gas and fine dust particles, the tale points away from the sun due to the pressure of solar radiation and the solar wind. This alignment, known as the anti-solar direction, distinguishes it from the tails of asteroids or inactive comets. The tail's composition reflects the comet's internal structure. Heavier molecules like carbon dioxide and carbon monoxide linger closer to the nucleus, while lighter species like hydrogen and helium are swept farther out. This stratification offers clues about the thermal history of the comet's surface, revealing where and when sublimation occurred. The chemistry of 3I Atlas is a Rosetta Stone for understanding the diversity of planetary systems. In our own solar system, comets from the Oort cloud and Kuiper belt are thought to originate from the protoplanetary disk, the swirling mass of gas and dust that gave birth to the planets. Their compositions reflect the temperature and density gradients of that disk, with the outermost regions preserving the coldest, most pristine materials. 3I Atlas, by contrast, comes from a system where the protoplanetary disk may have been shaped by different stellar neighbors, magnetic fields, or even supernova shocks. The abundance of carbon dioxide and the scarcity of water ice suggest that its parent system was colder or richer Inch's carbon-bearing molecules, a hypothesis supported by its high vertical velocity component, watts in 18.5 kilometers per second, which indicates it formed Inch's a region far from the galactic midplane. Moreover, the detection of cyanide and nickel vapor Inch's 3I Atlas's coma raises intriguing questions about the role of heavy elements Inch's interstellar chemistry. In the early solar system, such compounds were rare, but Inch's 3I Atlas, they appear Inch's concentrations comparable to those seen Inch's some solar system comets. This similarity implies that the processes governing the distribution of heavy elements may be universal, occurring Inch's the shockwaves of supernovae or the winds of dying stars. If so, then 3I Atlas is not just a relic of its home system, it is a messenger from the cosmic cycle of death and rebirth, carrying the echoes of stellar explosions that predate the sun. Perhaps most profound is the realization that 3I Atlas's journey is not unique. If interstellar comets are as common as simulations predict, then our solar system may be a crossroads for these travelers, a cosmic intersection where the histories of distant stars converge. Each new discovery brings us closer to answering fundamental questions. How do planetary systems form? What determines their chemical diversity? And how often do the seeds of life, water, organics and metals drift between stars? For now, 3i Atlas offers a tantalizing glimpse into these mysteries. Its icy heart, a beacon of the unknown. Yet, for all its revelations, 3i Atlas is only a beginning. Its origin inches the thick disk of the Milky Way, its ancient age, and its peculiar chemistry point to a broader narrative, one that spans the history of our galaxy and the fate of its stars. In the next segment, we will trace the comet's path back to its birthplace, unraveling the story of its journey through the galactic abyss and the clues it leaves behind. To understand 3i Atlas's origin is to embark on a journey through the annals of cosmic time. Its trajectory, a hyperbolic arc drawn by the sun's gravity, is a map of its travels, not just through the solar system, but through the galactic wilderness. By tracing this path backward, astronomers have pinpointed a region, inches the Milky Way's thick disk, a relic of the galaxy's earliest days. Here, among the oldest stars, 3i Atlas was born. Its nucleus forged inches the cold, dark nurseries of a distant stellar system. But what forces propelled it from its home to our doorstep? And what can its journey tell us about the turbulent history of the Milky Way? The thick disk of the Milky Way is a cosmic archive, a layer of stars that predates the younger, flatter, thin disk inches, which our sun resides. These stars, born over 10 billion years ago, orbit the galactic center inches tilted, eccentric paths, their motions influenced by the gravitational tides of mergers and collisions. 3i Atlas's origin inches this region is evident from its velocity components. A high radial velocity, UN 51.0 kilometers per second, suggests it is moving away from the galactic center, while its vertical velocity, MOTS 18.5 kilometers per second, indicates it is ascending above the galactic plane. Together, these values paint a picture of a comet born inches a system that has long since wandered far from the Milky Way's central hub. The thick disk stars are metal poor compared to those inches the thin disk, a reflection of the early universe's scarcity of heavy elements. Yet 3i Atlas's coma contains a surprising abundance of carbon dioxide and complex organic molecules, suggesting that its parent system was enriched by later stellar processes. This contradiction hints at a dynamic history. Perhaps the comet formed inches a region where supernova shocks or neutron star mergers seeded the interstellar medium with carbon-rich material. Or maybe its system was perturbed by a nearby giant star, scattering icy bodies into interstellar space. Whatever the cause, 3i Atlas is a relic of a galactic epoch when the Milky Way was young, violent, and still coalescing from the primordial chaos of the universe. The comet's estimated age, between 7.6 and 14 billion years, adds another layer to its enigma. At this age, 3i Atlas predates the solar system by over 3 billion years, placing its formation inches an era when the Milky Way was still assembling its present structure. If it survived for so long, it must have endured countless encounters with other stars, each one a potential threat to its stability, yet somehow, it remained intact. Its nucleus preserved inches a deep freeze until the sun's warmth reawakened it. This resilience speaks to the durability of comets, their icy hearts shielded by layers of refractory materials and volatile ices. Even inches the harsh vacuum of interstellar space, where cosmic rays and stellar winds erode unprotected surfaces. 3i Atlas endured. The origin of 3i Atlas challenges our understanding of how interstellar objects are distributed inches the galaxy. Earlier models predicted that most interstellar visitors would hail from the solar apex, the direction inches which the sun is moving through the galaxy. But 3i Atlas's southern origin defies this expectation. This discrepancy raises questions about the symmetry of the Milky Way's thick disk and the mechanisms that launch comets into interstellar space. Are there regions of the galaxy where such ejections are more common? Do certain stellar environments favor the production of interstellar comets? The answers may lie inches the upcoming detections of other interstellar objects, which could reveal patterns, inches, their origins and trajectories. Furthermore, 3i Atlas's journey offers insights into the long-term stability of planetary systems. Most comets, inches the solar system, originate from the Oort cloud, a spherical shell of icy bodies extending tens of thousands of AU from the Sun. These comets are occasionally nudged into the inner solar system by passing stars or galactic tides. 3i Atlas, by contrast, never belonged to such a reservoir. Its hyperbolic trajectory suggests it was ejected from its parent system. Inches a single violent event, perhaps a close encounter with a giant planet or a stellar flyby. If such ejections are common, then the galaxy may be awash inches interstellar comets, their numbers dwarfing those inches the Oort cloud. This possibility transforms our view of the cosmos. Rather than isolated systems, stars may be connected by a continuous exchange of material, a cosmic conveyor belt ferrying fragments of one world to another. Finally, 3i Atlas's ancient age invites speculation about the early universe. If comets can survive for billions of years, inches interstellar space, then others may be even older, dating back to the formation of the first galaxies. Could such primordial comets contain the building blocks of life, amino acids, nucleotides? The idea is speculative, but the detection of complex organics, inches 3i Atlas's Comet, suggests that the chemistry of life may be more universal than once thought. If comets are indeed cosmic couriers, then the seeds of biology may have traveled between stars long before the first planets formed. As 3i Atlas fades from view, its legacy endures, a fleeting but profound encounter with the unknown. Yet, this is only one chapter, inches the story of interstellar comets. In the next segment, we will look to the future, examining how upcoming missions and technologies will deepen our understanding of these cosmic travelers and their role, inches the grand tapestry of the universe. The passage of 3i Atlas is a fleeting moment, inches the grand chronicle of the cosmos, but its impact will resonate far beyond its brief appearance. As the comet vanishes from Earth's view, it leaves behind a trail of questions, challenges, and possibilities. What other interstellar visitors await discovery? How will new technologies reshape our ability to study these objects? And what can they reveal about the origins of life and the structure of the Milky Way? The future of interstellar exploration hinges on these questions, and the tools being developed today promise to unlock answers that once seemed beyond reach. The next frontier, inches interstellar comet research, lies inches the capabilities of emerging observatories and missions. The Vera C. Rubin Observatory, set to begin operations inches the 2020s, will revolutionize the detection of faint, fast-moving objects like 3i Atlas. With its 8.4-meter mirror and 3,200 megapixel camera, the observatory will conduct the Legacy Survey of Space and Time, LSST, scanning the entire southern sky every few nights. This unprecedented cadence will enable astronomers to spot interstellar comets and asteroids with ease, even if they are as faint as magnitude 24.5. By comparing LSST data with existing surveys, researchers hope to identify patterns, inches the arrival rates and trajectories of these objects, shedding light on the distribution of planetary systems, inches the galaxy. Space-based missions will also play a crucial role. The European Space Agency's ESA proposed Comet Interceptor mission, scheduled for launch inches the late 2020s, aims to intercept a pristine comet, inches the outer solar system, or an interstellar visitor. Unlike traditional comet missions, which target known objects, Comet Interceptor will remain dormant until an interstellar candidate is identified, at which point it will activate and pursue the target. This strategy ensures that the mission can study a truly unaltered interstellar object, providing insights into its composition, structure, and activity. Similarly, NASA's Lucy and Psyche missions, while focused on asteroids, will test technologies and operational strategies that could be adapted for future interstellar exploration. Ground-based networks, such as the global relay of observatories watching transients happen, growth, will enhance our ability to respond rapidly to discoveries. By linking telescopes across multiple continents, growth enables real-time follow-up observations of transient events, including interstellar comets. This coordination is essential for tracking objects like 3i Atlas, which may disappear from view within weeks. Additionally, Advances Inch's machine learning and artificial intelligence will automate the detection and classification of interstellar objects, reducing the reliance on manual searches and increasing the efficiency of data analysis. The proliferation of interstellar comet studies will transform our understanding of planetary formation and the chemical evolution of the galaxy. By comparing the compositions of interstellar comets with those Inch's the solar system, scientists can determine how planetary systems vary Inch's different stellar environments. For example, if future interstellar comets exhibit similar chemical signatures to 3I Atlas, it could indicate that carbon-rich, metal-poor systems are common Inch's the thick disk. Conversely, if they show greater diversity, it would suggest that planetary formation is highly variable, shaped by local conditions such as stellar winds, supernova proximity, and galactic location. These studies will also refine our models of the Milky Way's structure and history. The trajectories of interstellar comets act as traces of galactic dynamics, revealing how stars and their planetary systems migrate over time. By mapping the origins of these objects, astronomers can reconstruct the Milky Way's merger history, identifying the remnants of ancient satellite galaxies and the pathways of star formation. Furthermore, the discovery of older interstellar comets, potentially dating back to the formation of the first galaxies, could provide direct evidence of the universe's early chemistry, offering clues about the emergence of complex molecules Inch's the prestellar-interstellar medium. Perhaps most excitingly, interstellar comets may hold the key to understanding the origins of life. The detection of amino acids, nucleobases, and other organic molecules Inch's 3I Atlas's Comet suggests that the building blocks of biology are not unique to the solar system. If future missions confirm that interstellar comets frequently deliver these materials to young planetary systems, it could support the theory that life's precursors are widespread Inch's the cosmos. This perspective shifts the search for extraterrestrial life from a quest for habitable planets to a broader inquiry into the dispersal of life's ingredients across the galaxy. As 3I Atlas recedes into the void, it leaves behind a legacy of curiosity and discovery. Its arrival was a reminder that the universe is not a static expanse, but a dynamic web of connections, where stars trade fragments of their worlds and comets serve as ambassadors from distant systems. The tools and techniques developed to study 3I Atlas are just the beginning. They open the door to a new era of interstellar exploration, one Inch's which we will not merely observe the cosmos but engage with it. In the coming decades, as more interstellar visitors arrive and are studied, we will come to see ourselves not as isolated inhabitants of a single solar system, but as participants Inch's a galactic conversation that has been ongoing for billions of years. The universe, it seems, is speaking, and finally, we are learning to listen. In the vast, silent expanse of the cosmos, where galaxies spiral like whirlpools of light and stars burn for eons, a single object moved with purpose. Discovered on 1 July 2025, 3I Atlas, later designated CEAS 2025 N1. Atlas was not born Inch's the solar system. Instead, it hailed from the distant reaches of the Milky Way, a relic from a time when the galaxy itself was young. Its arrival marked a fleeting encounter, a cosmic ballet between a wandering comet and our sunlit neighborhood. As the third interstellar object ever confirmed, 3I Atlas carried secrets older than Earth itself, secrets that demanded the attention of humanity's sharpest eyes turned skyward. The story of 3I Atlas begins not with a dramatic spectacle, but with a quiet flicker Inch's the night sky. Detected by the Asteroid Terrestrial Impact Last Alert System, Atlas, telescope Inch's, Chile, this interloper entered the inner solar system at a staggering speed of 58 kilometers per second, a velocity far exceeding the escape velocity of the Sun. Its trajectory, hyperbolic Inch's shape, betrayed no allegiance to the gravitational embrace of our star. Instead, it was a transient guest, destined to return to the interstellar void after a brief fiery passage. Yet, even Inch's its brevity, 3I Atlas offered a glimpse into the ancient architecture of the galaxy, a testament to the dynamic, interconnected nature of the universe. This comet, though faint and distant, became a symbol of humanity's relentless curiosity. Its discovery was not merely an achievement, Inch's observation, but a reminder of how much remains unseen. Inches the dark. For centuries, humans have gazed upward, seeking meaning. Inches the constellations and tracking the movements of celestial wanderers. With 3i Atlas, that quest took on new urgency. What else might lurk beyond the edge of our cosmic backyard, waiting to be found? The detection of 3i Atlas was a triumph of technology and vigilance. The Atlas system, designed to scan the skies for potentially hazardous asteroids, operates on a principle of patience and precision. Each night, its twin telescopes, Inches Chile and Hawaii, capture wide-field images of the heavens, comparing them against previous observations to spot moving objects. On that fateful evening, Inches July 2025, a faint smudge, Inches the constellation Sagittarius, stood out, not for its brightness, but for its motion. Moving at 61 kilometers per second, the object defied expectations, its path diverging sharply from the predictable orbits of asteroids and comets native to the solar system. Initial confusion reigned among astronomers. The object's apparent magnitude of 18 placed it far below the threshold of naked eye visibility, requiring powerful telescopes to confirm its existence. Yet its trajectory told a tale of interstellar origins. Calculations revealed a hyperbolic excess velocity, the speed needed to escape the sun's gravitational pull, of 58 kilometers per second. No solar system body could achieve such a velocity without an external force, and none of the planet's gravitational tugs could account for this. The evidence pointed inexorably to a visitor from beyond. The confirmation process unfolded as a symphony of collaboration. Professional observatories, such as the Zwicky Transient Facility, ZTF, Inches California, and the Hubble Space Telescope, joined forces with amateur astronomers like Sam Dean, whose meticulous analysis of archival data uncovered pre-discovery observations dating back to late June 2025. These images buried Inches the dense star fields near the galactic center, had gone unnoticed due to the region's visual clutter. Dean's insight that the comet's passage coincided with the Milky Way's crowded heart highlighted the challenges of spotting interstellar objects. For a time, 3i Atlas lingered on the near-Earth object confirmation page, its identity uncertain until follow-up observations clarified its true nature. By 2 July 2025, the International Astronomical Union's Minor Planet Center had classified 3i Atlas as an interstellar comet, assigning it the designation 3i. This nomenclature honored its place in Inches history as the third such object, following the enigmatic 1i Oumuamua Inches 2017. Yet 3i Atlas posed unique mysteries. Unlike its predecessors, it did not approach Earth closely enough to raise alarms, nor did it exhibit the cigar-like shape of Oumuamua. Instead, it behaved like a classic comet, its coma a glowing envelope of gas and dust, revealing its icy heart beneath. The journey of 3i Atlas through the solar system was one of revelation. As it neared perihelion on 29 October 2025, its nucleus, cloaked Inches a coma spanning thousands of kilometers, began to unravel its secrets under the sun's intense heat. Observations by the Hubble Space Telescope and the James Webb Space Telescope painted a picture of a primordial object, rich Inches volatile compounds. Carbon dioxide dominated its composition, a stark contrast to the water-rich comets of our own solar system. Traces of water ice, carbon monoxide, and even cyanide gas hinted at a chemistry shaped by the cold, turbulent environments of its birthplace. Yet the most astonishing discovery lay Inches 3i Atlas's age. Studies of its orbital mechanics revealed that it hailed from the Milky Way's thick disk, a population of ancient stars formed billions of years before the solar system. By tracing its velocity components, astronomers calculated that 3i Atlas could be anywhere from 3 to 14 billion years old, making it potentially twice as ancient as Earth. Such an age suggested that the comet had witnessed epochs of galactic evolution, surviving supernovae, stellar collisions, and the slow drift of star clusters. If it bore the same chemical signatures as the first generation of stars, it might hold clues to the building blocks of life itself. Its origin, Inches the southern celestial hemisphere, further defied expectations. Previous interstellar objects had arrived from the direction of the solar apex, the path of the sun's motion through the galaxy. 3I Atlas, however, came from the opposite quadrant, a region where telescopes struggled to penetrate the dense, dusty veil of the galactic center. This anomaly raised profound questions. Was 3I Atlas a fluke, or did the galaxy harbor countless such wanderers hidden in its plain sight? Could its southern origin indicate a richer diversity of interstellar objects, or perhaps a bias inches our observational capabilities? As 3I Atlas passed Mars inches October 2025, robotic orbiters captured fleeting glimpses of the comet's tail, its cyanide emissions glowing faintly inches the Martian twilight. From that vantage point, the comet appeared as a ghostly specter, a traveler from a forgotten epoch now drifting toward its final act. Its hyperbolic path ensured it would never return, a one-way voyage through the solar system and back into the interstellar abyss. And yet, inches its brief visit, 3I Atlas left an indelible mark on human understanding. What made 3I Atlas behave like a comet rather than an asteroid? The answer lies inches its heart, a frozen nucleus of ice and rock, warmed by the sun's rays to release a cascade of gases and dust. But unlike the familiar comets of the solar system, 3I Atlas's chemistry told a story of alien origins. Its abundance of carbon dioxide, coupled with traces of exotic molecules like carbonyl sulfide, suggested a formation environment unlike anything inches our corner of the galaxy. This interstellar wanderer was not merely a cosmic tourist, it was a time capsule, preserving the conditions of a distant stellar nursery. As we turn our gaze inward, the next chapter of 3I Atlas's tale awaits. What can its volatile composition teach us about the early universe? How does its journey reshape our understanding of planetary formation across galaxies? The answers lie inches the stars, and perhaps inches the silent echoes of 3I Atlas's passage. In the vast, silent expanse of the cosmos, where stars burn like distant sentinels and galaxies spiral inches endless dance, a solitary traveler arrived inches our corner of the universe. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, stationed inches Rio Hurtado, Chile, captured the fleeting glow of an object, unlike any seen before. Designated 3I Atlas, this interstellar comet hurtled toward the inner solar system at an astonishing 58 kilometers per second, over 200,000 kilometers per hour. Its trajectory a hyperbolic arc that betrayed its origin beyond the sun's gravitational embrace. As it approached, the comet carried with it the whispers of a star system long vanished. Its icy heart, a relic of the Milky Way's ancient past, the discovery of 3I Atlas marked a pivotal moment in human history. It was the third confirmed interstellar visitor, joining the enigmatic 1I Oumuamua 2017 and 2I Borisov Nash 2019, and the first to exhibit the unmistakable signs of a comet, a glowing coma and a tail sculpted by solar winds. Yet its significance extended far beyond mere novelty. 3I Atlas was a time capsule, a fragment of another world's infancy, offering clues to the chemistry and dynamics of distant stellar nurseries. Its arrival was a reminder that our solar system is not isolated, but part of a grand cosmic exchange, where objects traverse the void as messengers of the universe's deepest secrets. As scientists turned their telescopes skyward, they realized they were witnessing something extraordinary. Here was an object born inches the shadow of the Milky Way's galactic center, older than our own solar system, now passing through our cosmic neighborhood. Its journey spanned billions of years, a voyage punctuated by the silent collisions of stars, the gravitational tides of the galaxy, and the slow erosion of time. What could this frozen wanderer reveal about the birth of planets, the evolution of stars, and the shared heritage of all matter inches the cosmos? The answers lay hidden inches its frosty nucleus, waiting to be unveiled by the light of the sun. At its core, 3I Atlas is a dynamic interplay of ice and fire, a delicate balance between the forces that shape it and the void that surrounds it. Like all comets, it consists of a solid nucleus, a mixture of rock, organic compounds and frozen gases, and a transient coma, a gaseous envelope that forms as the sun's radiation heats the nucleus. The nucleus itself remains shrouded in mystery, its true size obscured by the luminous haze of the coma. However, observations by the Hubble Space Telescope suggest that the nucleus spans between 0.32 and 5.6 kilometers diameter, with the most probable estimate hovering below 1 kilometer. This minuscule core belies the comet's immense significance, for within its frozen depths lie the chemical fingerprints of a star system's early days. As 3I Atlas approaches the Sun, its surface begins to warm, triggering a process called sublimation, the direct transformation of solid ice into gas. This phenomenon releases a cascade of volatile molecules, including carbon dioxide, water vapor, carbon monoxide, and carbonyl sulfide. The James Webb Space Telescope, JWST, with its unparalleled sensitivity to infrared wavelengths, detected these substances in remarkable detail. Notably, carbon dioxide dominates the comet's emissions, a stark contrast to most solar system comets, where water ice is the primary driver of activity. This anomaly hints at a formation environment with a distinct chemical profile, possibly one where carbon-rich materials prevailed over oxygen. Ground-based observatories, such as the Very Large Telescope MILT, uncovered further surprises. Cyanide gas and atomic nickel vapor were identified in the coma, their concentrations mirroring those observed in comets within our own solar system. These findings challenge assumptions about the homogeneity of interstellar objects, suggesting that the building blocks of planetary systems may share universal similarities, or perhaps diverge in ways we have yet to comprehend. The presence of cyanide, a molecule central to prebiotic chemistry, raises tantalizing questions about the universality of life's precursors. The comet's age, estimated at 7 to 14 billion years, adds another layer of intrigue. Traced back to the Milky Way's thick disk, a region inhabited by ancient stars, 3I Atlas predates the solar system by at least 3 billion years. The thick disk's inhabitants are relics of the galaxy's youth, their compositions marked by lower metallicity, a scarcity of heavy elements. This places 3I Atlas in a cosmic cradle, where star formation was slower and more chaotic, a stark contrast to the relatively recent, metal-rich environments where our solar system coalesced. Its journey through the galaxy has been a lonely one, shaped by the gravitational tides of the Milky Way and the random encounters of stellar neighbors. Even its trajectory tells a story. With a hyperbolic excess velocity of 58 kilometers per second, 3I Atlas entered the solar system at speeds far exceeding those of native objects. This velocity, combined with its path traced back to the direction of the galactic center, confirms its extraterrestrial origin. Unlike the previous interstellar visitors, which hailed from the solar apex, the direction of the sun's motion through the galaxy, 3I Atlas emerged from the opposite hemisphere. This unexpected origin defied predictions, suggesting that interstellar objects may hail from a broader range of galactic regions than once believed. The chemical composition of 3I Atlas is not merely a curiosity, it is a Rosetta Stone for understanding the diversity of planetary systems. The dominance of carbon dioxide over water ice, the presence of cyanide and nickel, and the absence of certain expected volatiles all point to a formation environment distinct from our own. In our solar system, comets from the Kuiper Belt and Oort cloud typically carry a higher proportion of water, shaped by the conditions of the protoplanetary disk that birthed them. 3I Atlas, however, seems to originate from a star-forming region where carbon-rich materials were more abundant, perhaps inches a disk with a different temperature gradient or chemical history. This disparity challenges the notion that all planetary systems follow a uniform evolutionary path. If 3I Atlas is indeed a product of the thick disk's ancient, low metallicity environment, it implies that the building blocks of planets vary depending on their galactic birthplace. Such variation could influence the prevalence of habitable worlds, the chemistry of atmospheres, and even the emergence of life. The comet's cyanide emissions, for instance, are reminiscent of the organic molecules that predate life on Earth. raising the possibility that the seeds of biochemistry are scattered across the galaxy. Moreover, the comet's age offers a glimpse into the early universe. At 7 to 14 billion years old, 3I Atlas predates the solar system by a factor of 2, making it a witness to epochs when the Milky Way was young and star formation was rampant. The thick disk, from which it hails, is a relic of the galaxy's violent past. Collisions between proto-galaxies, the collapse of massive molecular clouds, and the slow accretion of matter over eons. Studying 3I Atlas allows scientists to probe these ancient processes, reconstructing the galactic history that shaped the stars and planets we see today. Yet the comet's journey is not without peril. Its high velocity and hyperbolic path mean it will escape the solar system entirely, never to return. By October 2025, as it reaches perihelion at 1.36 AU from the Sun, the comet will pass through the region between Earth and Mars, its closest approach to our star. From Earth, however, it will remain a faint, elusive target, its brightness capped at magnitude 11.5. Observers must contend with its proximity to the Sun, which will obscure it during critical phases of its passage. Only through the ingenuity of robotic observatories and the patience of dedicated astronomers will its secrets be fully revealed. The implications of 3I Atlas extend beyond science. It is a humbling reminder of our place inches the cosmos. A tiny fleeting moment inches the life of a universe, teeming with stories untold. Every atom inches our bodies, every star inches the night sky, is connected by threads of time and space. In 3I Atlas, we see a reflection of ourselves, a traveler from a distant past converging with a present we share. Its passage is not an end but a beginning, a call to explore, to question, and to marvel at the infinite complexity of existence. As 3I Atlas fades from Earth's view, another world prepares to take its measure. Mars, with its thin atmosphere and unobstructed vantage point, will soon host an unprecedented observation. By October 2025, the comet will pass within a mere 1.36 AU of the Sun, its path carrying it closer to the red planet than to Earth. From Mars' surface and orbiting satellites, the comet will shine at magnitude 11, a faint but detectable glow against the Martian twilight. This unique opportunity will allow instruments aboard the Perseverance rover and the Mars Reconnaissance Orbiter to analyze the comet's spectrum, probing its composition with a precision impossible from Earth. While Earthbound observers strain to catch glimpses of this interstellar visitor, Mars' robotic eyes will offer a clearer portrait of its nature. The data gathered will refine our understanding of 3I Atlas's chemistry, its interaction with solar radiation, and its role inches the cosmic cycle of matter. In this exchange of knowledge, we find a profound truth. The universe reveals itself not inches isolation, but through the collective gaze of all who seek to understand it. As 3I Atlas departs our solar system, it leaves behind more than observations. It leaves a legacy of curiosity, a testament to the boundless connections that bind us to the stars. And so, the story continues. Beyond Mars, beyond the confines of our own backyard, the galaxy beckons. What other travelers await discovery? What other fragments of ancient worlds will cross our path? The answer lies inches the vast uncharted darkness, a darkness not empty, but alive with the echoes of creation, the whispers of time, and the promise of wonders yet unseen. In the vast, silent expanse of the cosmos, where time stretches into epochs and distances defy comprehension, the solar system occasionally receives envoys from beyond. These are not the familiar travelers bound by the sun's gravity, but wanderers from distant stars, carrying secrets of their birthplaces etched into their icy nuclei. On 1 July 2025, such a visitor was spotted by the Asteroid Terrestrial Impact Last Alert System MACH Atlas telescope at Rio Hurtado, Chile, a glowing ember drifting through the inner solar system, its path a stark departure from the elliptical orbits of native comets. This interstellar comet, designated 3I Atlas, marked itself as the third confirmed interstellar object to grace humanity's telescopic gaze, joining the enigmatic 1I Oumuamua and 2I Borisov inches a celestial trilogy of cosmic outliers. What makes 3I Atlas extraordinary is not merely its origin, but the story it tells of the universe's ancient past. As it hurtles inward at 58 kilometers per second, faster than any object-borne inches our own system, it challenges us to rethink the interconnectedness of galaxies. Its arrival is a reminder that the Milky Way is a dynamic tapestry of motion, where stars and their attendant debris drift through space, occasionally colliding with the gravitational threads of neighboring systems. For a fleeting moment, 3i Atlas becomes a beacon of cosmic curiosity, a transient guest whose journey spans billions of years, and whose chemistry hints at the primordial soup of another stellar cradle. To witness 3i Atlas is to stand at the intersection of science and wonder. It is a relic of a forgotten epoch, older than our solar system, carrying with it the volatile compounds and frozen histories of a faraway corner of the galaxy. As it approaches perihelion, the point of closest approach to the Sun, it will become a fleeting spectacle, visible only to instruments trained on the heavens. Yet its true significance lies not inches its brightness, but inches the questions it ignites. What shaped this comet? Inches its home system. How many others like it wander unseen? And what can its passage teach us about the origins of life, the architecture of galaxies, and the shared destiny of stars? 3i Atlas's journey begins inches the outer reaches of the galaxy, where the gravitational tides of the Milky Way gently nudge objects, like comets and asteroids, into trajectories that escape their home systems. Unlike the comets of our own solar system, which originate from the Kuiper belt or the distant Oort cloud and follow elliptical paths around the Sun, 3i Atlas is unbound. Its trajectory is hyperbolic, a mathematical curve that describes motion on a collision course with the Sun before slingshotting back into interstellar space. With a hyperbolic excess velocity of 58 kilometers per second, it moves at a speed that defies the Sun's gravitational pull, a velocity too great to be explained by interactions with planets or other solar system bodies. This alone confirms its interstellar provenance. The comet's discovery by the Atlas system underscores the importance of automated surveys, inches detecting such rare phenomena. When first observed on 1 July 2025, 3i Atlas was already deep within the inner solar system, traveling at 61 kilometers per second relative to the Sun. Its position 4.51 AU from the Sun, between the orbits of Jupiter and Saturn, placed it inches a transitional zone where solar heating begins to awaken cometary activity. As sunlight warms its nucleus, volatile ices such as carbon dioxide, water, and carbon monoxide sublimate into gas, carrying dust particles into a luminous coma. This process, captured by the Hubble Space Telescope, revealed a nucleus likely smaller than 1 kilometer inches diameter, its light obscured by the surrounding haze. Spectroscopic analyses by the James Webb Space Telescope and the Very Large Telescope have further unraveled the comet's chemical identity. Unlike solar system comets, which are typically rich inches water and methane, 3i Atlas is dominated by carbon dioxide, suggesting a formation environment colder than even the Kuiper belt. The presence of cyanide gas and atomic nickel vapor adds another layer of mystery. These elements are rare inches our solar system's comets, but may reflect the unique conditions of its stellar birthplace. Such findings challenge assumptions about the universality of cometary chemistry and hint at the diversity of planetary systems beyond our own. Yet 3i Atlas remains elusive inches. Some respects, its exact origin is inferred from its trajectory, which traces back to the direction of the galactic center, inches the constellation Sagittarius. Here, within the Milky Way's thick disk, a dense ancient region populated by stars billions of years old, the comet likely formed. The thick disk's high vertical velocity component, watts plus 18.5 kilometers per second, indicates that 3i Atlas follows a tilted orbit relative to the galactic plane, a hallmark of objects ejected from this ancient stellar population. Age estimates place it between 3 and 14 billion years, making it potentially twice as old as the solar system. This raises profound questions. How long has it traveled? What cataclysmic event inches its home system sent it adrift? And how many others like it remain hidden inches the galactic dark? The study of 3i Atlas transcends mere curiosity. It is a portal into the history of the Milky Way, unlike 1I Oumuamua, which offered little more than a geometric riddle, and 2I Borisov, whose similarity to solar system comets hinted at a shared heritage. 3I Atlas stands apart. Its southern origin, contrary to early predictions that interstellar objects would predominantly hail from the sun's direction of motion, the solar apex, suggests that the galactic distribution of such wanderers is more complex than previously imagined. This discrepancy challenges models of interstellar object dynamics and implies that the Milky Way's thick disk, a reservoir of ancient metal-poor stars, may be a more prolific source of ejected debris than expected. The comet's age, if the 7.6 to 14 billion year estimate holds, places it enters the era when the Milky Way was still coalescing from primordial gas clouds. In such an environment, young stars would have frequently perturbed each other's orbits, flinging comets and asteroids into the void. 3I Atlas may have been born during a galactic collision or a violent supernova explosion, events that could have stripped it from its parent system. Its survival over eons is a testament to the resilience of these objects, which endure the harsh vacuum of interstellar space until they chance upon a new system to visit. For scientists, 3I Atlas is a Rosetta Stone of stellar archaeology. Its isotopic ratios, if measurable, could reveal the composition of its stellar nursery, offering clues about the chemical evolution of the galaxy. The detection of cyanide and nickel vapor, for instance, may indicate a formation environment rich in heavy elements, a signature of a star that lived and died long before the solar system existed. Moreover, its hyperbolic trajectory provides a rare opportunity to map the gravitational influences of nearby stars, refining our understanding of how interstellar objects are distributed across the galaxy. Yet perhaps the most tantalizing aspect of 3I Atlas is its potential to inform the search for life. Comets are often considered cosmic couriers of organic molecules, and while 3I Atlas's carbon-rich chemistry is intriguing, its lack of water ice complicates this narrative. Does this imply that life's building blocks are not universal, or that 3I Atlas's home system lacked the necessary conditions for such chemistry to thrive? Alternatively, could its journey through interstellar space have altered its composition? These questions linger, unresolved, as the comet continues its lonely voyage. As 3I Atlas approaches perihelion on 29 October 2025, its visibility from Earth wanes. The sun's glare obscures it from terrestrial telescopes, leaving us to rely on indirect measurements and the faint hope of capturing glimpses during twilight. Yet the red planet, Mars, offers an unexpected vantage point. At its closest approach to the comet, Mars will lie just 0.36 AU away, a distance where the comet's coma, glowing with carbon dioxide and dust, will shine at magnitude 11 inches, Martian skies. For orbiters like NASA's Perseverance rover and the European Space Agency's ExoMars Trace Gas Orbiter, this is an unprecedented opportunity to study an interstellar visitor up close. Mars orbiters, equipped with spectrometers and cameras, could analyze the comet's composition inches ways impossible from Earth. They might detect organic molecules inches its coma, trace the dynamics of its outgassing, or even map the nucleus's shape and rotation. Such data could reveal whether 3I Atlas's chemistry is truly alien or shares roots with the solar system's comets. More profoundly, the mission could test the hypothesis that interstellar comets carry prebiotic materials, seeding the ingredients for life wherever they travel. But to understand where 3I Atlas came from and why it chose this path, we must look beyond the comet itself. Its trajectory, traced back through the stars, leads us to the heart of the Milky Way, to the ancient thick disk where time flows differently and the echoes of the galaxy's youth persist. To unravel this story, we must peer into the past, guided by the comet's velocity and the gravitational fingerprints it leaves behind. 3I Atlas is more than a transient streak of light inches the night sky. It is a messenger from a forgotten epoch, a relic of the Milky Way's turbulent history, and a harbinger of the vast interconnected web of stellar systems that span the cosmos. Its passage reminds us that the universe is not a static expanse, but a living, breathing entity, where objects migrate, collide, and evolve. As we track its journey from the cold depths of interstellar space to the fiery embrace of the Sun, we are not merely observers but participants. Inches a grand cosmic dialogue. In the coming months, as Mars's orbiters turn their instruments toward this interstellar wanderer, and as Earthbound telescopes strain to catch its final whispers, we will glean fragments of a story older than our own. 3i Atlas may vanish from view, but its legacy will endure. Inches the data it leaves behind, inches the questions it inspires, and inches the realization that we are not alone. Inches the universe, only temporarily, and only inches isolation. In the boundless expanse of the cosmos, where stars flicker like ancient sentinels and galaxies spiral inches silent dances, a solitary traveler emerged. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, Station Inches Oreo Hurtado, Chile, captured the first glimpse of a celestial wanderer hurtling through the inner solar system. Designated 3i Atlas, this interstellar comet became the third known visitor to traverse the gravitational embrace of the Sun since humanity first detected such phenomena. Unlike the familiar comets born inches the Kuiper Belt or Oort cloud, 3i Atlas carried no ties to our cosmic neighborhood. Its arrival was a whisper from the furthest reaches of the Milky Way, a message etched inches ice and gas, bearing secrets from a time before our solar system's birth. As 3i Atlas approached, it revealed itself as a fleeting specter of the universe's primordial past. With a hyperbolic trajectory and a velocity exceeding 58 kilometers per second, it defied the Sun's pull, destined to escape back into the void. Yet, inches its brief passage, it offered a glimpse into the chaotic beauty of interstellar space, a realm where comets, asteroids, and rogue planets drift as remnants of stellar nurseries long dissolved. For scientists and dreamers alike, 3i Atlas became a cosmic enigma, a relic from a distant epoch, carrying the echoes of a galaxy's ancient history. This script embarks on a journey to unravel the mysteries of 3i Atlas. From its discovery to its origins, inches the Milky Way's thick disk. We will explore how this interstellar wanderer reshapes our understanding of the universe. Through the lens of science and imagination, we will trace its path, decode its composition, and ponder the profound implications of its existence. To understand 3i Atlas's origin, we must first decipher the cosmic language of motion. The comet's trajectory, a hyperbolic curve that curves sharply around the Sun before escaping into the void, speaks volumes. Unlike the elliptical paths of solar system comets, which loop back to their icy reservoirs, 3i Atlas's path is unbound, a signature of an object born beyond the Sun's gravitational dominion. Its velocity, measured at 58 kilometers per second relative to the Sun, exceeds the escape velocity of the solar system, confirming its interstellar provenance. But how do scientists pinpoint its exact origin? The answer lies inches the comet's velocity vector, broken into three components: radials u, transverse Blice volts, and vertical Blice watts, motion relative to the galactic plane. By analyzing these components, researchers reconstructed 3i Atlas's path backward through the Milky Way. The results were startling. The comet hailed from the galaxy's thick disk, a region teeming with ancient stars. The thick disk, a warped and tilted structure spanning the galaxy, hosts some of the oldest stellar populations, stars over 10 billion years old, their surfaces laced with the remnants of early supernovae. What sets 3i Atlas apart from its predecessors, 1i Oumuamua and 2i Borisov, is its vertical velocity component, watts Ponce 18.5 kilometers per second. This high value suggests it does not orbit the galaxy inches a flat plane, like most stars, but instead follows a chaotic inclined path. Such trajectories are characteristic of the thick disk, where gravitational interactions with massive structures, such as the galactic bar or dark matter halos, have perturbed stellar orbits over eons. By tracing this motion, astronomers concluded that 3i Atlas's home lies inches a region of the Milky Way, where time has stood still, preserving the raw materials of a bygone era. Further evidence emerged from spectroscopic analyses. Observations by the James Webb Space Telescope revealed an unusual richness inches carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These volatile compounds, preserved for billions of years, hint at a formation environment vastly different from the solar system's. Meanwhile, the Very Large Telescope detected cyanide gas and atomic nickel vapor, elements typically associated with extreme stellar processes. Together, these clues paint a picture of a comet forged inches a stellar nursery, where young stars birthed planets from primordial disks, only for its parent body to be ejected into the interstellar abyss. Yet, 3I Atlas's discovery was not without surprises. Unlike Oumuamua and Borisov, which originated from the solar apex, the direction of the sun's movement through the galaxy, it came from the southern celestial hemisphere. This defied expectations, as southern origin interstellar objects were thought to be rarer due to observational biases and the density of stars inches that region. The comet's arrival challenged assumptions about the distribution of interstellar material, suggesting that the galaxy's thick disk may be a prolific source of such wanderers, hidden inches plain sight by the glare of the galactic center. If 3I Atlas is indeed 7 to 14 billion years old, it predates the solar system by 3 to 8 billion years. This staggering age raises profound questions. What conditions allowed it to form so long ago? And what does its survival imply about the resilience of interstellar comets? The thick disk, where 3I Atlas was born, offers a window into the galaxy's earliest days. Here, molecular clouds collapsed under gravity to form the first generations of stars, their lives ending inches cataclysmic supernovae that seeded the cosmos with heavy elements. Amid this turmoil, comets like 3I Atlas likely formed inches the icy outskirts of protoplanetary disks, later ejected by gravitational tides or stellar encounters. The comet's composition provides further insight. Its abundance of carbon dioxide and scarcity of water ice suggest it formed inches a colder, denser region than the solar system's outer edges. In the thick disk's frigid depths, temperatures may have been low enough for carbon dioxide to condense directly onto dust grains, forming a snow line akin to the solar system's water snow line. Such environments would have fostered the creation of complex organic molecules, precursors to life. If 3I Atlas carries these building blocks, it becomes a cosmic courier of primordial chemistry, offering clues about the universality of life's ingredients. Moreover, 3I Atlas's journey challenges our understanding of interstellar objects' lifetimes. Most comets disintegrate upon entering the inner solar system, their volatile ices sublimating under the sun's heat. Yet 3I Atlas, despite its rapid approach, retained a detectable coma and nucleus. This resilience hints at a dense, cohesive structure, possibly shielded by layers of refractory material. Could such comets survive countless traversals of the galaxy, carrying the memory of their birthplaces across eons? If so, the Milky Way may harbor a vast, invisible archive of ancient worlds, waiting to be discovered. The implications extend beyond astronomy. 3I Atlas invites us to reconsider our place. Inches the cosmos. We are not alone, inches our quest for origins. The same forces that shaped Earth, starlight, ice, and the dance of gravity have sculpted countless other worlds. Now adrift inches the dark. Each interstellar visitor is a testament to the interconnectedness of the universe, a reminder that the building blocks of life may have traveled across galaxies before finding a home inches our corner of the cosmos. Yet, for all its revelations, 3I Atlas posed a riddle. Why did it arrive from the south? The solar apex, the direction of the sun's motion through the galaxy, was once assumed to be the primary source of interstellar visitors. Models predicted that most such objects would originate from this region, where stellar encounters and galactic tides could eject comets into interstellar space. However, 3I Atlas defied these predictions, arriving from the opposite hemisphere. Was it a statistical anomaly, or did it expose a flaw inches our understanding? The answer may lie inches the thick disk's dynamics. Unlike the thin disk, where stars orbit the galaxy inches orderly paths, the thick disk is a turbulent realm. Here, gravitational interactions with the galactic bar and spiral arms warp stellar orbits, sending them careening into the halo or even beyond the galaxy. If 3I Atlas's parent star resided inches this chaotic zone, it could have been nudged onto an escape trajectory by a passing giant star or a supernova shockwave. Such events, though rare, are not unheard of inches the thick disk's violent history. Additionally, observational biases may have skewed earlier assumptions. The galactic center, from which 3I Atlas emerged, is a star-drenched region, where distinguishing a faint comet from a background star is akin to spotting a firefly inches a floodlit stadium. Only the Atlas system's automated surveys, capable of scanning the entire sky, could pluck it from the crowd. This raises the tantalizing possibility that many more southern origin interstellar objects await discovery. Hidden inches the glare of the Milky Way's heart, as 3I Atlas hurtles toward its perihelion inches. October 2025. Its path will take it beyond Mars, offering a fleeting opportunity for spacecraft to study its composition inches unprecedented detail. Yet, even as it vanishes from our view, its legacy endures. It is a bridge between epochs, a fragment of the galaxy's youth now woven into the fabric of our own cosmic story. And as future generations peer into the night sky, they may find another interstellar wanderer, another messenger from the dark, carrying its own tale of creation, destruction, and the eternal cycle of the cosmos. In the grand theater of the cosmos, where stars are born and die inches cycles spanning eons, humanity has long sought patterns to decipher the universe's secrets. For decades, astronomers built models to predict the origins of interstellar travelers, those rare objects ejected from alien solar systems, drifting through the void like silent messengers. These models, refined by decades of observation, suggested that such visitors would most often arrive from the north, the direction of the solar apex, the point toward which our solar system hurtles through the Milky Way. But when 3I Atlas pierced the heavens inches July 2025, it defied expectation. Born from the southern celestial hemisphere, its arrival was not a whisper, but a thunderclap, a challenge to assumptions that had shaped generations of astrophysics. Why does this matter? Because the cosmos is not a static stage. It is a dynamic, ever-shifting expanse where probabilities shift like sand underfoot. The fact that 3I Atlas emerged from the south, a region long considered a blind spot, inches our telescopic gaze, forces us to confront a fundamental question. Are we seeing the universe as it is, or as our tools allow us to perceive it? The discovery of 3I Atlas is not merely about a comet. It is a mirror held up to the limits of human knowledge, reflecting the biases embedded inches our methods. As we trace the comet's path through the stars, we uncover not just its story, but our own. To understand why 3I Atlas's origin is so unexpected, we must first grapple with the geometry of our cosmic neighborhood. The solar system, like all stars inches the Milky Way, is inches perpetual motion. Our local group of stars orbits the galactic center at approximately 230 kilometers per second, a velocity that defines the solar apex, the direction of our collective journey through the galaxy. Models of interstellar object trajectories predict that the majority of these wanderers would originate from the same direction, as stellar encounters and galactic tides eject debris preferentially along the path of least resistance. Yet 3I Atlas arrived from the opposite quadrant, a region of the sky dominated by the dense star fields of the galactic center. Here, the Milky Way's thick disk, a sprawling ancient population of stars older than the solar system itself, crowds the view, rendering faint objects nearly invisible. Telescopes scanning for interstellar visitors face a paradox. The very regions where such objects might originate are also the most observationally hostile. The southern hemisphere, home to the galactic bulge's chaotic glow, becomes a cosmic crossroads where signals are drowned inches noise. The discovery of 3I Atlas inches the constellation Sagittarius, near the galactic center, underscores this challenge. Early observations by the Atlas telescope at Rio Hurtado revealed the object at a faint magnitude of 18, barely distinguishable from the surrounding stellar clutter. Even with follow-up data from the Zwicky Transient Facility ZTF and the Very Large Telescope, confirming its interstellar nature required unraveling a web of pre-discovery images. The comet's trajectory, traced back through calculations of its hyperbolic excess velocity, revealed a radial velocity component, u of 51.0 kilometers per second, and a vertical velocity, watts of punts 18.5 kilometers per second, numbers that placed its origin firmly inches the thick disk's ancient domain. This revelation highlights a critical asymmetry inches our observational capabilities. While northern sky surveys dominate due to the concentration of major observatories inches the northern hemisphere, the southern skies remain undersampled. 3i Atlas's discovery, therefore, is not just a triumph of technology, but a reminder of the blind spots inches our cosmic vision. Its path, once shrouded by the Milky Way's glare, now compels us to re-evaluate how we define the boundaries of the observable universe. The implications of 3i Atlas's southern origin ripple far beyond its immediate discovery. For one, it calls into question the statistical models used to estimate the frequency of interstellar objects. Previous studies, based on the trajectories of 1i Oumuamua and 2i Borisov, assumed a roughly equal distribution of interstellar visitors from all directions. However, 3i Atlas's emergence from the south suggests that either these models are incomplete or that southern origin interstellar objects are more numerous than anticipated. Consider the work of Matthew Hopkins and his collaborators, who analyzed 3i Atlas's velocity components to estimate its age. By comparing the comet's motion to the kinematics of the thick disk, a population of stars with low metallicity and high vertical velocities, they concluded that 3i Atlas could be between 7.6 and 14 billion years old. This places it inches the realm of primordial relics, predating the solar system by billions of years. If correct, such an age challenges our understanding of the timescale for planetary formation and the mechanisms by which interstellar objects are ejected. Could 3i Atlas have formed inches a now vanished protoplanetary disk, only to be hurled into the interstellar void by a violent stellar encounter? Or does its extreme age hint at a different origin altogether, such as the fragmentation of a distant ancient star? Meanwhile, independent analyses by Asta Taylor and Daryl Seligman offer a broader perspective. Their study, which simulated the trajectories of hypothetical interstellar objects, found that southern origin visitors, like 3i Atlas, should occur at a rate consistent with current observations. This suggests that our models may have underestimated the number of southern interstellar objects, not because they are rare, but because detecting them requires overcoming the observational hurdles posed by the galactic center. The implication is profound. The true census of interstellar visitors may be far richer than we imagine, hidden inches plain sight by the Milky Way's own luminosity. But this realization also demands humility. For centuries, humanity has gazed upward, seeking to map the heavens with precision. Yet the universe resists easy categorization. 3i Atlas's discovery is a testament to the power of serendipity inches science, a reminder that even inches an era of advanced instrumentation, the cosmos retains its capacity to surprise. To capture the full breadth of interstellar visitors, we must adapt our methods, deploying more telescopes inches the southern hemisphere, refining algorithms to detect faint signals against crowded fields, and embracing the possibility that our assumptions are incomplete. As 3i Atlas hurtles through the solar system on its hyperbolic trajectory, its path is a thread woven into the vast gravitational tapestry of the Milky Way. The forces that shaped its journey, stellar encounters, galactic tides, and the unseen pull of dark matter, form a cosmic choreography that governs the fates of all interstellar travelers. Understanding this dance is the next frontier inches unraveling the mystery of 3i Atlas. For while its southern origin challenges our assumptions, its ultimate destiny lies inches the hands of gravity itself, the universal force that binds the stars and sculpts the cosmos. In the next segment, we will explore how gravitational interactions across the galaxy dictate the trajectories of interstellar objects, revealing the hidden architecture of the Milky Way, from the gentle tugs of neighboring stars to the explosive ejections caused by binary systems. We will examine the cosmic processes that hurl comets like 3i Atlas into the interstellar void, and what these processes might tell us about the birth and death of planetary systems across the universe. In the vast tapestry of the cosmos, Where stars blaze like distant lanterns and galaxies spiral inches silent waltzes, a solitary traveler emerged from the shadows of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas inches the arid expanse of Chile's Rio Hurtado. 3I Atlas became the third confirmed interstellar object to traverse our solar system. Its arrival was not merely a scientific curiosity, but a profound reminder of the universe's boundless interconnectedness. Named after the vigilant Atlas network that first glimpsed its faint glow, this comet carries whispers of epochs long past. Its journey spanning billions of years across the Milky Way, the solar system, often perceived as a self-contained realm, is now understood as a porous frontier. Before 3I Atlas, two other interstellar travelers had passed through. 1I Oumuamua inches 2017, a cigar-shaped enigma that defied easy classification, and 2I Borisov inches 2019, a more conventional comet that revealed familiar chemistry amid alien origins. Yet 3I Atlas stands apart. Its trajectory, its speed, and its composition paint a picture of a cosmic nomad, born inches a forgotten corner of the galaxy, a relic from a time when the Milky Way itself was young. As scientists and stargazers alike turned their instruments toward this fleeting guest, they gazed not just at a comet but at a bridge between worlds, a testament to the dynamic, ever-shifting nature of the universe. To comprehend 3I Atlas's origins, one must first grasp the physics of its journey. The comet's path is defined by a hyperbolic trajectory, a mathematical curve that describes an object moving faster than the escape velocity of the body it approaches. For the Sun, this threshold is approximately 42 kilometers per second at the distance of Earth, yet 3I Atlas hurtles through space at 58 kilometers per second, a velocity so great that it cannot be bound to our star system. This excess speed is its defining feature, a cosmic fingerprint that declares its interstellar birthright. Such velocities are not born of chance. In the chaotic cradles of star systems, gravitational interactions can act as cosmic slingshots. Imagine a binary star system, where two suns orbit each other inches a delicate balance. Amper's passing object, be it a planet, moon, or comet, might be captured by one star's gravity, only to be ejected violently by the gravitational tug-of-war between the two. Similarly, the migration of planets inches a young system can destabilize smaller bodies, flinging them into the void. These processes, though rare, are not uncommon on galactic scales. Every star system likely sheds debris over time, scattering remnants into the interstellar dark. 3I Atlas's velocity components further unravel its story. In the galactic coordinate system, its motion is characterized by a radial component, u of nit 51.0 kilometers per second, and a vertical component, watts of plus 118.5 kilometers per second, relative to the Sun. These numbers indicate that the comet approached the solar system from the direction of the Milky Way's thick disk, a region populated by ancient stars, their orbits tilted and wandering compared to the thin disk where younger stars like our Sun reside. The thick disk's slower rotation and higher vertical velocity mean that objects within it drift upward and outward relative to the galactic plane, a path 3I Atlas follows with eerie precision. Confirming its interstellar origin required meticulous orbital calculations. By tracing its position over weeks, astronomers reconstructed its trajectory back through the stars. Pre-discovery images from the Zwicky Transient Facility and Atlas itself revealed its path long before its official detection. These data showed that 3I Atlas had no gravitational interactions with planets inches our solar system, capable of altering its course. Its motion was too pristine, too unyielding to have been shaped by anything within the heliosphere. Instead, it was a relic of the galaxy's deeper history, a wanderer untethered by any star's embrace. The implications of 3I Atlas's journey ripple far beyond its own story. If ejections from star systems are commonplace, the galaxy may be teeming with rogue comets and asteroids, their surfaces etched with the chemistry of their homeworlds. These objects could serve as cosmic carriers, carrying organic molecules, water, or even microbial spores between planetary systems. The theory of panspermia, the idea that life's building blocks might hitchhike across space, gains new weight inches the presence of such interstellar travelers. While 3I Atlas itself is unlikely to harbor life, its composition offers tantalizing clues about the conditions inches its birthplace. Observations by the James Webb Space Telescope, JWST, reveal that 3I Atlas is unusually rich inches carbon dioxide, a volatile compound rarely detected inches abundance, inches, solar system comets, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. This mix suggests a formation environment colder and more chemically diverse than the Kuiper belt. The Very Large Telescope's detection of cyanide gas and atomic nickel vapor further complicates the narrative. Cyanide, a key ingredient, inches the synthesis of amino acids, and nickel, essential for certain enzymes, hint at a chemistry that may mirror the early stages of planetary evolution. Elsewhere, inches the galaxy. Yet perhaps the most staggering revelation lies inches the comet's age. Studies led by Matthew Hopkins and Asta Taylor estimate that 3I Atlas is between 7.6 and 14 billion years old, far older than the 4.6 billion-year-old solar system. This places its origin inches the Milky Way's thick disk, a population of stars that formed inches the galaxy's infancy. These stars, forged inches the chaos of the Milky Way's earliest days, are metal-poor and ancient. Their orbits steeped inches the gravitational memory of a younger universe. To find a comet from such an epoch is to hold a fragment of galactic history, a time capsule from an era when the first stars and planets coalesced. What does this mean for our understanding of the cosmos? 3I Atlas challenges the notion of the solar system as a static, isolated entity. It reminds us that our neighborhood is a transient way station, inches a galactic sea of motion. Every comet that crosses our path is a messenger from another star system, a fleeting encounter, inches the grand theater of stellar evolution. And if 3I Atlas is any indication, the galaxy's history is written, not just inches its stars, but inches the silent journeys of its discarded children. But how do we know, with certainty, that 3I Atlas is truly interstellar? The answer lies inches the mathematics of its motion. Orbital mechanics, the language of celestial navigation, distinguishes between objects bound to the sun and those free to roam the galaxy. Ampere's Keplerian orbit, elliptical, parabolic, or hyperbolic, is determined by an object's energy relative to the gravitational field it traverses. For 3I Atlas, the calculation is clear. Its orbital energy is positive, meaning it possesses sufficient kinetic energy to escape the sun's pull entirely. This distinction is not trivial. In the early days of 3I Atlas's discovery, its trajectory raised concerns among astronomers. Initial data suggested it might approach Earth's orbit, prompting its temporary listing on the Near-Earth Object Confirmation page. Yet follow-up observations revealed a different truth. The comet's path was never destined to intersect with Earth's. Instead, it followed a hyperbola that carried it into the outer solar system and beyond. By the time it reached perihelion on 29 October 2025, it would be 1.36 AU from the Sun, closer than Mars, but far from Earth, and then it would vanish, its speed ensuring it would never return. The confirmation of 3I Atlas's interstellar origin hinged on these precise calculations. By integrating its observed positions over time, astronomers reconstructed its entire journey, from its arrival inches the inner solar system to its eventual departure. The result was a trajectory that originated inches the direction of Sagittarius, near the Milky Way's galactic center, and extended into the galactic halo, a region where the gravitational influence of the Milky Way weakens, allowing objects to escape. This mathematical rigor transformed 3I Atlas from a mere point of light into a verified emissary of the stars. Yet the story does not end there. The same principles that confirm 3I Atlas's alien heritage also raise deeper questions. How many such objects have passed unnoticed through the solar system? What secrets do their compositions hold about the chemistry of other star systems? And if the galaxy is indeed a vast network of wandering comets, what might they reveal about the shared origins of life? These are the questions that await the next chapter of exploration, as humanity continues to peer into the depths of the cosmos, seeking answers written inches the language of light and motion. As 3I Atlas recedes into the void, its legacy endures. though it will never be seen again by human eyes. Its passage has left an indelible mark on our understanding of the universe. It is a reminder that we are not alone in the cosmos, that the stars, distant and silent, are connected by threads of ice and stone, each carrying stories of their own. In the quiet hum of its hyperbolic escape, 3i Atlas whispers of a universe inches motion, a place where nothing is truly lost, only transformed and reborn inches the endless dance of creation. In the vast silent expanse of the cosmos, where galaxies spiral like whirlpools of stardust and planets drift through the void, the universe reveals its secrets one fleeting glimpse at a time. Among these revelations, the arrival of interstellar visitors stands as a testament to the interconnectedness of the cosmos, a reminder that even the smallest speck of light can carry stories from distant corners of the galaxy. On 1 July 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope at Rio Hurtado, Chile, captured a glimmer that would soon ignite the imagination of scientists and dreamers alike. This glimmer, later designated 3i Atlas, was no ordinary comet. It was a traveler from beyond our solar system, hurtling through space at an astonishing 58 kilometers per second. Its trajectory a hyperbolic arc that defied the gravitational embrace of the Sun. 3i Atlas is the third confirmed interstellar object to traverse our celestial neighborhood, following the enigmatic 1i Oumuamua 2017 and the more recent 2i Borisov 2019. Yet, unlike its predecessors, 3i Atlas carries a unique signature. Evidence of its ancient origins inches the Milky Way's thick disk, a region teeming with stars billions of years older than our own. As it approaches perihelion, its closest point to the Sun on 29 October 2025, this comet becomes a cosmic messenger, offering clues about the birthplaces of stars, the evolution of planetary systems, and the invisible tides that shape the galaxy. To witness 3i Atlas is to stand at the threshold of the unknown, where science and wonder converge inches a dance of light and shadow. But the story of 3i Atlas is not merely one of discovery. It is a tale of precision, of numbers that chart the paths of celestial wanderers, and the equations that distinguish the familiar from the alien. It is a story of humanity's relentless quest to understand the universe, a quest that now turns its gaze toward a single fleeting object, whose journey transcends the boundaries of our solar system. To prove that 3i Atlas is truly interstellar, astronomers must decode the language of its motion. At the heart of this endeavor lies the concept of specific orbital energy, a measure that determines whether an object is bound to the Sun's gravity or free to roam the galaxy. For objects within our solar system, such as planets and comets from the Oort cloud, this energy is negative, indicating a closed elliptical orbit. But for 3i Atlas, calculations revealed a startling truth. Its specific orbital energy is positive. This means the comet's path is not a closed loop but a hyperbola, a trajectory that curves outward and escapes the Sun's gravitational pull entirely. The hyperbolic nature of 3i Atlas's orbit is further confirmed by its hyperbolic excess velocity of 58 kilometers per second. This speed exceeds the escape velocity required to break free from the Sun's influence, a value determined by the Sun's mass and the distance at which the comet enters the solar system. For comparison, Earth itself orbits the Sun at a mere 29.78 kilometers per second. If 3i Atlas had originated from within our solar system, such a velocity would require an impossible gravitational slingshot from a massive body, a scenario ruled out by its trajectory. Instead, the comet's speed and path are consistent with an object born inches another stellar system, flung into interstellar space by the violent processes of star formation or planetary upheaval. The confirmation of 3i Atlas's interstellar status was not immediate. When the Atlas telescope first detected it on 1 July 2025, the object appeared faint, with an apparent magnitude of 18 far beyond the range of naked eye observation. Initial calculations suggested a highly eccentric orbit that might bring it dangerously close to Earth, prompting the Minor Planet Center, MPC, to list it on the Near-Earth Object Confirmation page. However, follow-up observations from the Zwicky Transient Facility, the James Webb Space Telescope, and amateur astronomers like Sam Dean quickly painted a different picture. These data revealed that 3I Atlas's trajectory never brings it closer than 1.8 AU, 2070 million kilometers, to Earth, posing no threat. More importantly, they confirmed the comet's hyperbolic path, sealing its identity as a visitor from the stars. Yet the true marvel of 3I Atlas lies not only inches its motion, but inches its composition. Observations by the Hubble and James Webb Space Telescopes unveiled a nucleus cloaked inches a coma of gas and dust, with an estimated diameter of less than 1 kilometer. Spectroscopic analyses detected an unusual abundance of carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. Even more intriguingly, the Very Large Telescope observed emissions of cyanide gas and atomic nickel vapor, chemical signatures reminiscent of comets inches our own solar system. These findings suggest that 3I Atlas shares a chemical heritage with the building blocks of planets, raising profound questions about the universality of planetary formation processes. As 3I Atlas hurtles toward perihelion, its journey becomes a laboratory experiment, inches real time. The sun's heat will sublimate its icy nucleus, releasing jets of gas and dust that trace the comet's structure. For a brief moment, humanity will hold a front row seat to the disintegration of an object forged inches the crucible of another star system. And inches that moment, the numbers that define its motion, the angles of its approach, the velocity of its departure, will crystallize into a story of cosmic kinship. The origin of 3I Atlas is as enigmatic as its journey. By tracing its trajectory backward through the stars, astronomers have pinpointed its point of entry into the solar system, the direction of the constellation Sagittarius, near the Milky Way's galactic center. This region, a dense tapestry of stars and nebulae, is part of the galaxy's thick disk, a population of stars and objects that formed inches the early epochs of the Milky Way. Unlike the younger, metal-rich stars of the thin disk, thick disk stars are ancient, with compositions reflecting the primordial conditions of the universe. If 3I Atlas hails from this region, it could be at least 7 billion years old, older than the solar system itself. Such an age is staggering. To put it into perspective, the solar system is a mere infant at 4.6 billion years, while 3I Atlas predates even the formation of our sun. This makes the comet a relic from the galaxy's youth, a time when the Milky Way was still assembling itself from smaller satellite galaxies. Theories suggest that such ancient objects might have been ejected from their home systems during chaotic episodes of planetary migration or gravitational interactions with binary stars. Whether 3I Atlas was born inches a solar system like ours, or inches a more exotic environment, remains a mystery, but its survival over billions of years speaks to the resilience of cometary material. What sets 3I Atlas apart from its interstellar predecessors is its vertical velocity component. Unlike 1I Oumuamua and 2I Borisov, which approach the solar system from the plane of the Milky Way, 3I Atlas arrives from the southern celestial hemisphere, moving upward through the galactic plane at a velocity of 18.5 kilometers per second relative to the Sun. This unusual trajectory suggests that the comet belongs to the thick disk population, which orbits the galaxy on inclined or even retrograde paths. Such a finding challenges assumptions about the distribution of interstellar objects, which were previously thought to originate predominantly from the solar apex. The direction of the Sun's motion through the galaxy, the southern origin of 3I Atlas hints at a broader diversity, inches the sources of interstellar visitors, suggesting that our telescopes may have missed many such objects due to observational biases. The implications of this discovery ripple outward. If thick disk objects like 3I Atlas are more common than previously believed, they could provide invaluable insights into the chemical evolution of the galaxy. Their ancient compositions, preserved inches frozen nuclei, might hold records of the early universe's elemental abundances. Moreover, their trajectories could help map the gravitational influences of unseen structures, such as dark matter halos or dwarf galaxies, which shape the Milky Way's architecture. In this way, 3I Atlas is not just a comet, it is a key to unlocking the hidden history of the cosmos. Yet, for all its scientific promise, 3I Atlas remains elusive. Its faintness, peaking at an apparent magnitude of 11.5, means it is invisible to the naked eye and requires specialized instruments to track. From Earth, observers must contend with its proximity to the galactic plane, where dense star fields obscure its presence. Even the James Webb Space Telescope, with its unparalleled sensitivity, struggles to separate the comet's light from the surrounding chaos. Only inches the months following perihelion, when 3I Atlas re-emerges, inches the dawn skies of Earth and Mars, will its secrets begin to unfold. As 3I Atlas continues its celestial voyage, its journey underscores a paradox central to human exploration. The same tools that allow us to chart the cosmos also reveal our fragility. The mathematics that confirm its interstellar status, the precise calculations of velocity, energy, and trajectory are the same principles that govern planetary defense. While 3I Atlas poses no threat to Earth, its discovery highlights the importance of vigilance. Every day, thousands of near-Earth objects streak through the solar system, some with trajectories that could intersect with our planet. The difference between a harmless visitor like 3I Atlas and a potential hazard lies inches the precision of our models. This balance between curiosity and caution defines our relationship with the universe. We are both explorers and inhabitants, driven to understand the cosmos while seeking to protect our fragile existence within it. The study of interstellar objects, like 3I Atlas, is not merely an academic pursuit. It is a rehearsal for the future, a test of our ability to anticipate and respond to cosmic events. As the comet fades from view, its legacy endures, a reminder that the universe is vast, indifferent, and full of wonders waiting to be discovered. And so the story of 3I Atlas does not end with its departure. It begins anew, carried forward by the questions it leaves behind. What other travelers lurk inches the darkness? What secrets do they hold about the birth of stars and the fate of worlds? In the quiet hum of the cosmos, these questions echo, urging us onward. In the vast tapestry of the cosmos, where time stretches into epochs and distances defy comprehension, the arrival of 3I Atlas is a fleeting whisper, a visitor from the farthest reaches of the galaxy, discovered on 1 July 2025. This interstellar comet hurtles through the solar system like a traveler crossing an alien desert, its icy heart glowing faintly under the sun's gaze. For a brief moment, humanity's eyes turn skyward, drawn by the mystery of its origin and the promise of knowledge it carries. Yet amid the awe lies a primal question. Could this stranger, born among the stars, threaten our fragile blue world? The answer, as with many cosmic riddles, lies inches the dance of numbers and trajectories. The discovery of 3I Atlas ignited a flurry of calculations, a race to map its path through the heavens. Scientists, armed with telescopes and algorithms, worked tirelessly to decode its motion. What they found was both reassuring and profound. This comet, though ancient and alien, would never come close enough to Earth to pose a danger. Its hyperbolic trajectory, a graceful arc bent by the sun's gravity, would carry it swiftly through the inner solar system and back into the interstellar void. Yet even inches its harmlessness, 3I Atlas serves as a reminder of the universe's indifference to our concerns. It is a relic of a time long before Earth formed, a silent witness to the birth of galaxies, now passing through our cosmic neighborhood like a ghostly echo of eternity. As the comet's story unfolds, we are invited to reflect on the fragility of our existence and the resilience of human curiosity. The study of 3I Atlas is not merely about tracking an object inches the sky. It is about understanding our place inches a universe teeming with mysteries. And so, with the tools of science and the wonder of imagination, we embark on a journey to unravel the secrets of this interstellar wanderer. To comprehend the comet's journey, one must first grasp the language of celestial mechanics. 3I Atlas entered the solar system from the direction of Sagittarius, a constellation cradling the Milky Way's galactic center. Its arrival was marked by a velocity of 61 kilometers per second, a speed so immense that if it had struck Earth, it would have released energy equivalent to millions of nuclear bombs. Yet the comet's trajectory is not a collision course but a fleeting flyby. Orbital simulations, fed by data from 31 observatories, revealed that 3I Atlas would approach the Sun at a distance of 1.36 astronomical units (AU) on 29 October 2025, placing it between the orbits of Earth and Mars. More importantly, its closest point to Earth would be 1.8 AU, a vast expanse that renders any impact impossible. The key to this conclusion lies in the comet's hyperbolic orbit. Unlike the elliptical paths of most solar system objects, a hyperbola is an open curve, meaning the comet's gravitational interaction with the Sun is insufficient to trap it into a repeating orbit. Instead, the Sun's pull bends 3I Atlas's path slightly, accelerating it to a hyperbolic excess velocity of 58 kilometers per second. This velocity, combined with the comet's trajectory, ensures it will escape the solar system entirely by 2026, vanishing into the interstellar dark. The calculations are precise, derived from decades of observational data, and refined by the collective efforts of astronomers worldwide. The Minor Planets Center, MPC, the global hub for tracking celestial bodies, played a pivotal role in confirming 3I Atlas's fate. The comet's true nature emerged as follow-up observations poured in. Data from the Zwicky Transient Facility and the Very Large Telescope, among others, painted a clear picture. 3I Atlas is a transient interloper, destined to leave as swiftly as it arrived. The absence of perturbations from planets further solidified this conclusion. Jupiter, Saturn, and even Mars exerted negligible influence, leaving the comet's path unaltered by their gravitational tides. This meticulous analysis is a testament to humanity's ability to peer into the abyss and find patterns in chaos. The same techniques used to track 3I Atlas are employed to monitor asteroids that could pose a threat, underscoring the dual purpose of such studies. While 3I Atlas is harmless, its discovery sharpens our vigilance, reminding us that the skies are not always empty of danger. The study of 3I Atlas transcends its immediate implications. It is a window into the broader architecture of the Milky Way and the origins of celestial objects. Unlike the solar system's comets, which originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas hails from the galactic thick disk, a region populated by ancient stars older than our own. Its vertical velocity component, WILDEST 18.5 kilometers per second, indicates it does not orbit the Milky Way in harmony with younger stars, but rather drifts at an angle, a relic of the galaxy's turbulent youth. This suggests that interstellar comets may be far more common than previously believed, especially in regions where stellar dynamics eject debris into the void. Moreover, the comet's composition offers tantalizing clues about its home system. Spectroscopic analysis by the James Webb Space Telescope revealed an unusual richness in carbon dioxide, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules, forged in the cold crucibles of protoplanetary disks, hint at a formation environment distinct from the solar system's. The presence of cyanide gas and nickel vapor, detected by the Very Large Telescope, further complicates this picture, mirroring the volatile chemistry of comets like Halley's. Such similarities and differences challenge assumptions about the universality of planetary formation processes. If 3I Atlas's host star lacked heavy elements, how did it produce such a complex mix of compounds? Or perhaps its system experienced unique conditions, intense radiation, collisions, or interactions with passing stars, that shaped its chemistry in ways we've yet to fathom. Beyond science, 3I Atlas's discovery reinforces the importance of global collaboration in planetary defense. The comet's faintness and position near the galactic center, a region crowded with stars, made it difficult to detect until its trajectory was confirmed. This highlights the limitations of current surveys, particularly in the southern celestial hemisphere, where 3I Atlas originated. While telescopes like ATLAS and ZTF excel at spotting interstellar visitors, their northern focus may bias our understanding of their distribution. Future missions such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time will address this gap, scanning the entire sky with unprecedented sensitivity. Yet the greatest lesson from 3I Atlas is not about technology, but perspective. In the grand scale of the cosmos, The comet is a speck of dust adrift inches a sea of stars. Its 7-billion-year-old nucleus predates the solar system by nearly 3 times, carrying memories of a galactic epoch when stars were young and supernovae lit the night. To study such an object is to touch the past of the Milky Way itself, a humbling realization that reminds us how small we are inches the cosmic arena. As 3I Atlas continues its voyage, a new chapter begins inches October 2025, when it passes within 0.4 AU of Mars, though still a safe distance. This proximity offers a unique opportunity for observation. From the Martian surface, the comet would shine at apparent magnitude 11. Visible to orbiters equipped with sensitive instruments, scientists hope to analyze its coma and tail inches detail, probing the volatile composition of an interstellar object up close. Yet, questions linger. Could the comet's fragile nucleus disintegrate under the sun's glare? Might fragments rain down on Mars, leaving behind traces of alien chemistry? These possibilities, though speculative, underscore the duality of 3I Atlas's journey. It is both a harbinger of knowledge and a reminder of the unknown. As we prepare to study this cosmic traveler, we are reminded that every discovery opens new doors to mystery. In the next segment, we will delve into the risks and rewards of 3I Atlas's Martian encounter, exploring what happens when a relic of the galaxy brushes against the red planet. Note, this section constitutes approximately 1/3 of the total script. The remaining sections will follow the same structure, expanding on the comet's Martian encounter, its chemical secrets, and its implications for interstellar exploration. In the vast, silent expanse of the cosmos, comets drift like ancient mariners, their trajectories etched by the gravitational tides of stars and planets. Among them, 3I Atlas stands apart, a traveler from another stellar cradle, now hurtling toward the heart of our solar system. Its arrival, first glimpsed by the Atlas telescope inches July 2025, has ignited both scientific fervor and existential wonder. Yet as it nears the sun, a question lingers. Will 3I Atlas endure the trials of its passage, or will it succumb to the relentless forces that await? Comets are fragile things, fragile inches away that defies their colossal scale. They are not mere rocks, but icy conglomerates of dust, gas, and volatile compounds, held together by gravity's delicate grip. Their nuclei, dense cores of frozen material, are akin to loosely packed snowballs, vulnerable to the sun's searing touch. For 3I Atlas, a nucleus no larger than a kilometer inches diameter faces an ordeal unlike any inches its 7-billion-year history. The sun's heat will sublimate its ices, releasing plumes of gas and dust that form its luminous coma and tail. But this transformation is a double-edged sword. The same energy that reveals the comet's secrets could also unravel its structure, turning a celestial relic into a cascade of stardust. To witness this dance of creation and destruction is to confront the universe's paradoxes, the interplay of permanence and impermanence, of order and chaos. 3I Atlas, born inches the thick disk of the Milky Way, a realm of ancient stars, now finds itself inches a fleeting moment of visibility. Its fate is uncertain, but inches that uncertainty lies the essence of cosmic exploration, the pursuit of knowledge through observation, speculation, and reverence. At the heart of 3I Atlas's vulnerability lies the physics of sublimation. Unlike earthly ice, which melts into liquid water under heat, cometary ices, primarily water, carbon dioxide, and carbon monoxide, transition directly from solid to gas when warmed by sunlight. This process, known as sublimation, generates pressure within the nucleus, fracturing its brittle crust and releasing trapped volatiles. The James Webb Space Telescope's observations of 3I Atlas revealed an unusual abundance of carbon dioxide, suggesting a composition distinct from many solar system comets. Such anomalies hint at a formation environment far removed from our own, perhaps inches a protoplanetary disk colder and more chemically diverse than the one that birthed the planets. The nucleus itself remains enigmatic. While estimates place its diameter between 0.32 and 5.6 kilometers, the true size is obscured by the comet's coma, a glowing halo of gas and dust that blurs the boundary between core and atmosphere. Without precise measurements of mass and density, astronomers must infer its structural integrity. Amper's smaller, denser nucleus might withstand solar heating better than a larger, porous one. Yet 3I Atlas is likely sub-kilometer size, suggests a body loosely bound, its cohesion precarious. As the comet approaches perihelion on 29 October 2025, solar radiation intensifies. At 1.36 AU from the Sun, closer than Mars, but farther than Earth, it will face temperatures sufficient to trigger rapid outgassing. The resulting jets of gas and dust can act like thrusters, altering the comet's rotation and stressing its structure. If the nucleus fractures, the comet may split into fragments, each trailing its own tail of debris. Such events are not unheard of. The 2007 disintegration of Comet 17P/Holmes offered a glimpse into this violent process. Observatories like Hubble and the Very Large Telescope will scrutinize 3I Atlas for signs of instability. Sudden increases inches brightness, irregular tail structures, or the emergence of multiple nuclei could signal a breakup. Mars orbiters, positioned to observe the comet as it passes near the red planet, may capture critical data on its final moments. These efforts underscore a fundamental truth. The universe is a laboratory, and every comet is a subject. Inches and experiments spanning millennia. Should 3I Atlas disintegrate, the aftermath would offer unparalleled scientific insight. Amper's fragmented comet would reveal the internal structure of its nucleus, exposing layers of ice, rock and organic material preserved since its formation. Spectroscopic analysis of the debris could identify exotic compounds, shedding light on the chemistry of distant star systems. Moreover, the distribution of fragments would provide clues about the comet's mechanical properties, whether it was a single body or a cluster of loosely aggregated chunks. Yet such a scenario also carries a bittersweet irony. Amper's disintegration would transform 3I Atlas into a diffuse cloud of particles, reducing its visibility and complicating studies of its pristine composition. The tension between preservation and transformation mirrors humanity's own struggle to balance curiosity with conservation. In the end, the comet's legacy may lie not inches its survival, but inches the data it leaves behind, a cosmic diary of its journey. Philosophically, 3I Atlas invites reflection on impermanence. Billions of years ago, it formed Inches, a stellar nursery now long vanished. Now it traverses a system it will never revisit, destined to escape into interstellar space unless it succumbs to the sun's gravity. Its fragility resonates with our own transient existence. Like the comet, we are ephemeral beings navigating a universe of constant flux. To observe 3I Atlas is to witness the intersection of time and matter, a reminder that even the most ancient objects are not immune to change. This perspective deepens our appreciation of the cosmos. Every comet, asteroid, or rogue planet is a story written inches stone and ice, a testament to the universe's capacity to create, sustain, and dissolve. 3I Atlas, with its ancient lineage and uncertain fate, embodies this duality. It is both a relic of the past and a harbinger of the future, a bridge between what was and what could be. As 3I Atlas edges closer to the sun, its story becomes more than a scientific case study. It becomes a parable of resilience and vulnerability, a mirror held up to the universe's grand design. The questions it raises transcend astronomy. What does it mean to exist? Inches, a world of entropy? How do we assign meaning to objects that defy permanence? And what can these celestial wanderers teach us about our place? Inches, the cosmos. These inquiries will guide the next segment, where we turn from the mechanics of cometary disintegration to the broader philosophical implications of encountering an interstellar visitor. 3I Atlas is not merely a body of ice and rock. It is a messenger from the depths of time, carrying with it the whispers of a universe older than our own. Its journey, however brief, reminds us that we too are travelers, passing through a cosmos that is both infinite and intimate, eternal and ephemeral. This script balances scientific detail with lyrical prose, adhering to the requested structure while weaving Inches themes of cosmic wonder and existential reflection. Each section builds upon the prior, culminating Inches, a transition that bridges empirical observation and philosophical inquiry. In the vast, silent expanse of the cosmos, where time stretches into eons and space folds into dimensions beyond comprehension, 3i Atlas drifts, a solitary traveler, bearing secrets older than the solar system itself, discovered inches the summer of 2025. This interstellar comet is not merely a transient visitor, but a relic from the infancy of the Milky Way. Imagine a fragment of primordial stardust, forged inches, a distant stellar nursery, now hurtling through the inner solar system. Like a ghostly messenger from the dawn of galaxies, its arrival stirs a profound question. What stories does this ancient wanderer carry about the universe's earliest days? To gaze upon 3i Atlas is to peer through the veil of time. The comet's hyperbolic trajectory, its blistering speed of 58 kilometers per second, and its origin inches the thick disk of the Milky Way, paint a picture of an object that has traveled for billions of years. Unlike the icy wanderers of our own solar system, which are mere infants inches cosmic terms, 3i Atlas predates Earth, Mars, and even the Sun. It is a time capsule, a frozen archive of conditions that prevailed when the galaxy was young, when stars were born inches frenzied bursts and planets coalesced from turbulent disks of gas and dust. As it glides through the inner solar system, its faint glow hints at a history written inches the chemical signatures of its coma and the structure of its nucleus. To understand this comet is to unlock a window into the cosmic crucible, where galaxies and planetary systems were forged. Yet 3i Atlas is more than a scientific curiosity. It is a reminder of our place inches the universe, a humbling testament to the interconnectedness of all things. Just as the atoms inches our bodies were once forged inches the hearts of stars, this comet carries materials that may have shaped worlds far from home. Its journey through the solar system is a fleeting encounter, a momentary alignment of the cosmos that invites us to contemplate the grandeur of existence. In the quiet glow of its coma, we find echoes of a universe still unfolding, and inches its passage, a call to explore the unknown. 3i Atlas's story begins with its discovery inches the skies above Chile, where the Atlas telescope captured a faint smudge of light against the backdrop of the Milky Way. At first glance, the object seemed unremarkable. A speck inches the night, indistinguishable from countless asteroids and comets that populate the solar system. But as astronomers traced its path, the true nature of 3i Atlas emerged. Its velocity, measured at 61 kilometers per second relative to the Sun, defied the gravitational bonds of the solar system. The comet's trajectory was hyperbolic, a sharp open curve that would carry it back into interstellar space, never to return. Such a path could only be explained if 3i Atlas had originated from another star system, propelled by forces beyond our own. What makes 3i Atlas truly extraordinary, however, is its age. By analyzing its velocity components inches the galactic coordinate system, scientists determined that the comet hails from the Milky Way's thick disk, a region populated by ancient stars whose origins trace back to the galaxy's violent youth. The thick disk is a cosmic vault, a repository of material formed inches the early universe when the Milky Way was a chaotic star-forming cauldron. Here, stars were born inches dense clusters, and collisions between protoplanetary disks may have ejected icy bodies like 3i Atlas into the void. With an estimated age of 7 to 14 billion years, 3i Atlas predates the solar system by over twice its current age. It is a relic from an era when the Milky Way was still assembling its spiral arms, and the universe itself was a fraction of its present size. The comet's chemical composition further reinforces its status as a cosmic time capsule. Observations by the James Webb Space Telescope revealed an unusually high concentration of carbon dioxide inches its coma, alongside traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules are common inches comets within our own solar system, but their ratios and abundances differ subtly. For instance, the dominance of carbon dioxide over water ice suggests that 3i Atlas formed inches a colder, more distant environment than typical comets from the Kuiper belt or Oort cloud. Additionally, the presence of cyanide gas and atomic nickel vapor, detected by the Very Large Telescope, hints at a unique evolutionary history. These compounds are typically associated with the high-energy processes of stellar nurseries, implying that 3I Atlas may have originated inches a region of the galaxy where massive stars were forming and exploding inches supernovae. Even the structure of 3I Atlas's nucleus remains a puzzle. While its coma is clearly visible, the nucleus, a solid core of ice and rock, is obscured by the surrounding haze of gas and dust. Estimates suggest the nucleus is less than 1 kilometer-inches diameter, a modest size for an object that has endured billions of years of cosmic radiation and stellar winds. Yet this fragility belies its resilience. The fact that 3I Atlas has retained its volatile ices and molecular complexity despite its interstellar journey speaks to the protective power of its icy shell. Like a time-worn scroll preserved inches a sealed chamber, the comet's nucleus may hold organic molecules that once contributed to the chemistry of life inches another star system. The study of 3I Atlas compels astronomers to reconsider long-held assumptions about planetary formation. In our solar system, comets are often viewed as remnants of the protoplanetary disk that surrounded the young sun, their compositions reflecting the conditions of their birth. However, 3I Atlas's interstellar origin and ancient age challenge this model. If this comet formed inches a different galactic environment, one characterized by higher metallicity, denser star clusters, or more frequent supernova events, its composition could represent a distinct recipe for planetary building block. This raises a tantalizing question. Are the materials that shaped Earth and its neighbors universal, or are they the product of a rare cosmic accident? One possibility is that 3I Atlas hails from a region of the galaxy where planetary systems formed under extreme conditions. The thick disk from which the comet originates is a dynamic zone where stars are older, heavier, and more likely to host planets with unusual architectures. In such an environment, protoplanetary disks may have been enriched with heavy elements from previous generations of stars, leading to the formation of comets with chemically distinct profiles. Alternatively, 3I Atlas could be a product of a binary star system, where gravitational interactions ejected icy bodies into interstellar space. The comet's high vertical velocity component, which carries it far above and below the galactic plane, supports this hypothesis. If 3I Atlas is indeed a binary ejection, it would suggest that such systems are more efficient at producing interstellar debris than previously thought. Moreover, 3I Atlas's southern origin, a direction opposite to the sun's motion through the galaxy, adds another layer of complexity. Early models predicted that most interstellar objects would originate from the solar apex, a point inches the northern sky where the sun's movement through the galaxy creates a wind of interstellar material. The fact that 3I Atlas arrived from the south challenges these assumptions, suggesting that interstellar objects may be distributed unevenly across the galaxy. This could indicate that the Milky Way's thick disk is a more prolific source of interstellar debris than the thin disk, where younger stars like the Sun reside. If true, it would mean that the galaxy's oldest stars and their planetary systems play a critical role in shaping the interstellar medium. Perhaps the most profound implication of 3I Atlas is its potential to bridge the gap between stellar nurseries and planetary evolution. The comet's carbon dioxide-rich coma, for instance, mirrors the conditions found inches the cold, outer regions of protoplanetary disks, where volatile ices condense into solid form. This similarity implies that the processes governing the formation of comets, and by extension planets, are not unique to the solar system, but are repeated across the galaxy. Yet the differences in 3I Atlas's composition also highlight the diversity of planetary systems. If this comet once orbited a star inches the thick disk, its chemistry could reflect the unique conditions of that system, offering a glimpse into how life-friendly ingredients might arise in different galactic environments. As 3I Atlas continues its journey, its legacy lies not only in the data it provides, but in the questions it inspires. Will future interstellar visitors share its ancient origins, or will they reveal new chapters in the story of cosmic evolution? The answers may lie hidden in the light of their comas, waiting to be deciphered by the next generation of telescopes. As 3I Atlas fades from view, slipping beyond the reach of Earth-based telescopes and into the shadow of the sun, its presence lingers inches the minds of those who watched its brief apparition. For a fleeting moment, this ancient traveler became a symbol of the universe's boundless history, a bridge between the birth of galaxies and the fragile existence of life on Earth. Its journey reminds us that we are not isolated inches the cosmos, but part of a grand interconnected web of matter and energy, stretching across time and space. Yet, 3i Atlas also underscores our limitations. Despite our technological prowess, we can only glimpse a sliver of its story. Its nucleus remains shrouded inches mystery, its exact age debated among scientists, and its ultimate fate unknown. In this uncertainty lies a paradox. The more we learn about the universe, the more we realize how much remains beyond our grasp. But perhaps that is the essence of cosmic wonder, not to conquer the unknown, but to stand inches awe of it. As the comet vanishes into interstellar darkness, it leaves behind a quiet invitation to keep looking, to keep questioning, and to remember that every star, every planet, and every drifting comet is a chapter inches a story, far older and grander than ourselves. In the vast, silent expanse of the cosmos, where galaxies spiral inches slow, eternal waltzes, and stars are born from the remnants of their predecessors, there exists a peculiar sense of impermanence. Amidst this grandeur, the universe whispers its secrets to those who dare to listen. One such whisper came inches the form of 3i Atlas, an interstellar comet that briefly crossed our solar system. A transient visitor from the furthest reaches of the Milky Way, discovered inches the summer of 2025. This ancient wanderer carries with it a story that predates our own, a tale etched inches the very fabric of time. As it hurtled through the void, its icy nucleus glowing faintly under the sun's gaze, 3i Atlas became more than a scientific curiosity. It became a mirror, reflecting humanity's insatiable quest for understanding. What does it mean to encounter a celestial body older than our own planetary system? To witness something that has traveled across the galaxy for billions of years, only to pass through our neighborhood for a fleeting moment? 3i Atlas challenges us to reconsider our place inches the cosmic hierarchy, not as solitary beings adrift inches a cold, indifferent universe, but as participants inches an ongoing dialogue between matter, energy, and time. Its journey, though brief, inches the context of cosmic timescales, resonates with profound questions. What is the nature of our origins? How do we fit into the grand design of the universe? And perhaps most humblingly, how do we, as fleeting observers, contribute to the eternal story of the cosmos? This narrative begins with the discovery of 3i Atlas, a discovery that bridges the gap between the finite and the infinite. Yet, it does not end there. It invites us to explore the implications of this encounter, to grapple with the awe-inspiring reality that we are not alone inches the universe, not inches the sense of intelligent life, but inches the sense that the cosmos itself is alive with motion, memory, and mystery. As we follow the trail of this interstellar traveler, we find ourselves drawn deeper into the heart of the universe's greatest enigma. The search for meaning inches a world that defies comprehension. The story of 3i Atlas begins inches the arid deserts of Chile, where the asteroid terrestrial impact blast alert system Marcellus scans the skies with relentless precision. On 1 July 2025, the telescope at Rio Hurtado captured a faint smudge of light near the border of the constellations Serpens Cauda and Sagittarius, a point that upon closer inspection revealed itself to be moving against the backdrop of fixed stars. At a distance of 4.5 astronomical units, AU, from the Sun, this object was already racing inward at a blistering 61 kilometers per second, a velocity far exceeding the escape speeds of any known solar system body. Within days, follow-up observations confirmed what the initial data had hinted. 3i Atlas was not bound to the Sun. It was a traveler from another star system, hurtling through the vacuum of space with a hyperbolic trajectory that would carry it back into interstellar darkness. The comet's path is defined by a hyperbolic excess velocity of 58 kilometers per second, a speed so great that it cannot be explained by gravitational interactions within our solar system. Unlike asteroids or comets native to the Kuiper belt or Oort cloud, 3I Atlas was never captured by the sun's gravity. Instead, it entered our neighborhood as a free agent, a relic of a stellar nursery long since scattered by the forces of time and motion. Its origin traces back to the Milky Way's thick disk, a region teeming with ancient stars and the remnants of early galactic evolution. Here, inches the shadow of the galactic center, 3I Atlas likely formed around a now distant sun, its icy nucleus preserving chemical signatures from an era when the galaxy was young and volatile. Observations by the Hubble Space Telescope and the James Webb Space Telescope have unveiled the comet's hidden treasures. Its nucleus, shrouded inches a diffuse coma of gas and dust, is estimated to be between 0.32 and 5.6 kilometers diameter, a size that, while modest, belies its cosmic significance. Spectroscopic analyses reveal an unusual composition. 3I Atlas is rich inches carbon dioxide, with traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules, forged inches the cold crucibles of interstellar space, hint at the comet's birthplace, a region where stellar winds and supernova remnants sculpted the raw materials of planets. Even more intriguing is the detection of cyanide gas and atomic nickel vapor, compounds typically associated with the violent processes of stellar death. Such findings suggest that 3I Atlas is not merely a passive fragment of a distant world, but a time capsule carrying the fingerprints of its home system's turbulent history. The comet's journey through the inner solar system is equally remarkable. On 29 October 2025, it will reach perihelion, the point of closest approach to the Sun, at a distance of 1.36 AU, nestled between the orbits of Earth and Mars. Here, the Sun's radiation will intensify the comet's activity, sublimating its frozen layers and unleashing plumes of gas and dust into space. Yet, despite its proximity to the Sun, 3I Atlas will remain a faint object from Earth, its light dimmed by the glare of the solar wind. Telescopes on Mars, however, may offer a clearer view, capturing the comet as it dances near the red planet's orbit. This dual perspective, terrestrial and Martian, underscores the interconnectedness of our solar system, even as 3I Atlas reminds us of the broader cosmic web that binds all stars and worlds. Astronomers have determined that 3I Atlas is not an isolated anomaly. Since its discovery in 2017, humanity has identified 3 interstellar interlopers: 1I Oumuamua, 2I Borisov, and now 3I Atlas. Each of these objects carries a unique signature, a story written inches the languages of chemistry and orbital mechanics. 3I Atlas, inches particular, stands out for its age. Studies by Matthew Hopkins and Asta Taylor estimate that it is between 3 and 14 billion years old, placing it among the oldest known comets inches the galaxy. This staggering antiquity raises profound questions about the longevity of such bodies and the environments inches which they endure. Could 3I Atlas have survived the gravitational tides of the Milky Way for eons, only to arrive at our doorstep inches the final chapter of its journey? Or is it a recent cast-off from a nearby star system, still bearing the scars of its violent expulsion? The answers lie inches the data, but the questions themselves transcend science. They invite us to ponder the nature of time, the resilience of matter, and the improbable odds that brought this ancient traveler to our attention. 3I Atlas is not just a comet, it is a messenger from the deep past, a reminder that the universe is both vast and intimate, a place where the smallest grains of dust can hold the keys to cosmic truths. To observe 3I Atlas is to confront the paradox of our existence. We are creatures of finite lifespans, yet we seek to comprehend the infinite. We are bound to a single planet, yet we dream of touching the stars. The comet's passage through our solar system is a microcosm of this tension, a fleeting intersection of 2 scales, the infinitesimal and the infinite. For 3I Atlas, this journey is but a moment inches its long, lonely voyage. For us, it is a revelation, a glimpse into the cosmic dance that has unfolded for billions of years. This encounter compels us to reevaluate our place inches the universe. Are we merely spectators, passive observers of a grand spectacle? Or do we, as thinkers and explorers, play an active role in shaping our understanding of the cosmos? The answer, perhaps, lies in the act of observation itself. When we study 3i Atlas, we are not just collecting data, we are participating in a dialogue that transcends time and space. The light we see from the comet has traveled over 7 billion years to reach us, carrying echoes of a distant past. In turn, our interpretations of that light ripple outward, influencing how future generations perceive the universe. In this exchange, we become both students and teachers, learning from the cosmos while contributing to its evolving story. Yet this relationship is not without humility. 3i Atlas, with its ancient age and alien origins, dwarfs our collective history, the civilizations that have risen and fallen on Earth since the comet's formation could fill volumes of books, yet they are but a footnote in the life of this interstellar wanderer. It is a sobering realization that our species' entire scientific enterprise, all our triumphs and failures, exists within the blink of a cosmic eye. And yet, this humility is not a barrier to progress. It is a catalyst. The very act of seeking to understand 3i Atlas, of unraveling its mysteries, is a testament to the human spirit's capacity to rise above its limitations. Ambition, too, is stirred by this encounter. 3i Atlas is a reminder that the universe is not a static entity, but a dynamic, ever-changing realm. The same forces that shape the comet's trajectory, gravitational tides, stellar winds, and the slow drift of galaxies are the same forces that govern our own destiny. If a comet can travel across the galaxy for billions of years, surely humanity, armed with technology and imagination, can venture farther than we ever have before. The study of 3i Atlas is not merely an academic exercise. It is a stepping stone toward interstellar exploration. By decoding the comet's chemical composition and trajectory, we gain insights into the conditions of other star systems, preparing ourselves for the day when we might visit them firsthand. Moreover, 3i Atlas challenges us to think beyond the confines of our own solar system. For centuries, Earthbound astronomers have gazed at the stars, wondering about the possibility of life elsewhere. Now, with the discovery of interstellar objects, we know that the cosmos is a bustling neighborhood, populated by travelers. These objects are not just scientific curiosities, they are evidence of the galaxy's interconnectedness. They remind us that we are not isolated islands in a sea of stars, but nodes in a vast network of celestial relationship. This perspective shifts our focus from competition to collaboration, from fear to curiosity. If a comet from the thick disk of the Milky Way can reach us, then perhaps one day we can reach it, and others like it. The implications of this shift are profound. They require us to rethink our priorities, to invest not just in technology, but in the wisdom to use it responsibly. The study of 3i Atlas is a call to action, to protect our planet while reaching for the stars, to preserve our knowledge while expanding our horizons. It is a call to embrace the dual nature of our existence as both fragile and resilient, as both limited and limitless. In the end, 3i Atlas is more than a comet. It is a symbol of the human condition, a journey through time and space, marked by uncertainty, driven by curiosity, and illuminated by the hope of discovery. Its story is not complete, nor is ours, but as we stand beneath the eternal sky, watching this ancient traveler fade into the distance, we are reminded that the universe is not a void to be feared, but a frontier to be embraced. As 3i Atlas vanishes from our night sky, its legacy remains, a spark igniting the imaginations of scientists, philosophers, and dreamers alike. The comet's journey is a testament to the enduring power of curiosity, a reminder that the universe is not a static backdrop, but a living, breathing entity. Yet this is only the beginning. The study of 3i Atlas opens doors to countless questions. What other interstellar visitors await discovery? What secrets do they carry from their distant homeworlds? And how will our understanding of the cosmos evolve as we learn to read their messages? These questions lead us to the next frontier, the search for extraterrestrial life, the mapping of exoplanets, and the development of technologies that will one day allow us to travel beyond our solar system. Just as 3i Atlas has expanded our horizons, so too must we expand our ambitions. The universe is vast, but it is not unknowable. With each observation, each calculation, each leap of imagination, we draw closer to the truth that binds us all to the fundamental unity of existence. The cosmos calls to us, and we must answer, not as individuals, but as a species united by the shared desire to understand. Let us carry the lessons of 3i Atlas forward, not as relics of the past, but as guides for the future. For inches the stars, we find not just our origins, but our destiny.